Good morning, all. Right. So the first thing we want to do is finish our syllabus on data structures and algorithm. So we need to do few more, about three more sorting algorithms. Let's finish those. Then the syllabus is fully over. Okay. So let me open the note. Right. So far we have discussed two searching algorithms: the linear search and binary search. Binary search we implemented in two different ways. That is using recursion and also without recursion. Okay. So remember, linear search is n squared, log n algorithm, worst case. Uh, but binary search is log 2n, which is better than log n. Okay. It's better than log n. Now you must have very good understanding about this. What is n algorithm, log n algorithm, right? Because every time you eliminate half of that in binary search. Okay. So linear search is like this, on. Binary search is like this, which is for large data that it needs considerably less time, log 2n. So then we moved on to sorting algorithms. Sorting algorithms. So we discussed the interpolation algorithm as well. So interpolation algorithm is improvement over uh, interpolation search is improvements over binary search, because in binary search we always go to the middle, right? Whereas interpolation search we go proportionately, right? We can calculate whether we should go little bit more biased towards the end or towards the beginning, relative idea, because data is already sorted. Okay? That is therefore it's improved. It's log 2 log 2n, log 2 log 2n. Okay, fine. So then we moved on to sorting algorithms. So we subdivided sorting algorithms into simple sorting algorithms and advanced sorting algorithms. So simple sorting algorithms, we discussed three of those: uh, bubble sort, selection sort, and insertion sort. All three are ON squared algorithms. Why ON squared? We had nested loop, one loop inside another loop, and both these loops goes almost entire cycle. If you have 100 data, almost the second loop also, first loop always going, say, 1 to 100, 0 to 999. The second loop also goes almost, but as I mentioned, this insertion sort is better because this side is already sorted. The second inner loop doesn't need to go to entire thing. Okay, so therefore, out of these, in general, all are O n squared. This is the worst because so many swapping also there. This is the next best because only one swapping at the end. But the iterations are pretty much like that. But this is the best out of these three because we are adding the data to the sorted side. We can stop once we add it to the correct position. Right. So that is what we have done. Okay, so simple sorts, but all three are in general O n squared. Okay, right. So any questions on those? Right. So then we discuss the shell sort as well. If not, let me know. I think we discussed shell sort. So in shell sort, we break it into parts and then sort vertically. And then again merge it like this. Then it's somewhat sort, not perfect. And again break it, right? And again break it to a smaller size. And again merge it. And again break it to a smaller size. And finally we get it on two columns and again merge it. Still it is not 100% sorted. Every time we sort vertically. Still, it is not 100% sorted, but then you can use another normal sorting mechanism, one of these, so even something like quick sort or something. Okay. But anyway, it's not very popular, but just remember it's called uh, shell sort. Shell sort. Right. That is where we stopped. Okay. That is where we stopped. Today we move on to the advanced sorting algorithms. These sort algorithms are much faster. Basically, these algorithms are n log n algorithms, right? Not log n. Log n is binary search. Quicksort and merge sort are n log n algorithm. N log n is not as good as log n, right? But definitely, so it goes like this. This is n squared verse. No, I think it's even goes like this. Yeah, not like this. N squared is not like this. Sorry. N squared is something like this. You know how y is equal to x squared, right? So this is n squared algorithms, like the three sorting techniques we discussed so far. Log 2n is, anyway, log 2n is for the binary search, like this, and log 2n. These quick sort and merge sort, of course, this is for searching algorithm. Quick sort and merge sort is n log 2n. It's like this, better than this, but not as good as log 2n, which is anyway not a sorting algorithm, right? But it's definitely better than this. Okay, n log 2n. So merge sort, quick sort, both are n log 2n algorithms. So definitely better than quick other sorts like uh, bubble sort, selection sort, insertion sorts. Okay, right. So these two algorithms use. But out of these, yes, both are log 2n. Out of these, so quick sort is considered mm, better than merge sort. Right? It's just like I told you, insertion sort is better than selection and bubble sort, though all three are n squared. Okay. So similarly, both are n log n, but quick sort is better than merge sort. Okay, that is why we call it quick sort anyway. Right. Right. So both these sorting algorithms use divide and conquer approach. You break it into smaller problems and conquer the smaller problem. And when we conquer the smaller problem, effectively we have fix or uh, solve the big problem. Okay. So both are. So you know that if we can come up with such a solution, basically we can use recursion because smaller problem is similar to the bigger problem. Only thing is we have lesser number of data to work with. Okay. Right. First we will look at what is merge sort. Merge sort is very easy to understand. Anyway, both are very easy to understand. Merge sort and quick sort. Right. In merge sort, what we do is, uh, I'll come back to this later. In merge sort, what we do is, say we have set of data. Actually, last year paper also they had merge sort question. Say unsort data. We break it into two. Right? We break it into two parts. So then left side we have 7 to, this is not sorted, say 7294. Right side we have 3861. Just break it. Our data into say 100 data 50-50. Right? 80 data 40-40. If it is odd number, yes, one side can have one more data. And that is fine. Right? If it is 49, maybe 25 and 24. Okay. Right. So then we further divide it. Right. Now this has to four data. We break it into two data. It's 7294. This one 3861. And we keep doing that until we end up with two data. So once we ended up with two data, we stop it. That means if it is 100, 50, 50, 25, 25, right? 12 and 13, and so on. When we get two data only, we stop. And this happens recursively. Now you can see it's recursion, right? It's not linear recursion also. And once you get into the two situation, then we sort those two data. So this is not sorted because 2 is smaller than 7. So then we sort it like 2 and 7. Right? So you need to swap it. If this is 9 and 4, we need to swap 4 and 9. 3 and 8 is already sorted. Don't do anything because it's already sorted. 6, 1, we need to swap 1, 6. Okay. So that is what we do. So that's the only operation we do at that level. Right. So now we have, uh, let me use a different color. Now we have 2, 7 and 4, 4, 9. Now these two we need to merge. Right? These two we need to merge. This and this. I will explain how to merge, which is very easy. So when you merge these two, you get merge means preserving the sorting nature. Okay. So it will be 2, 4, 7, 9. So right hand side branch also we do. Now this is 3, 8 is still 3, 8. 6, 1 will be 1, 6. Now we need to merge these two sorted arrays. And it will be 1, 3, 6, 8. Now we need to merge these two sorted. Now these are sorted arrays. So it will be 1, 2, 3, 4, 6, 7, 8, 9. So you can see in the return process, right? Return process, we keep merging two sorted arrays. Right? Merge into sorted arrays. Again, we need to merge these two sorted arrays. Get this. Okay. So that is how we do it. So this is now sorted. So now you can understand why we call it merge sort, right? Because we keep merging in the return. So once we do the sort, that is to sorting just two data. That is a clever way of sorting our data. And this is much better performance because we can do it in log 2 in time. Right? Right. So therefore, only thing is now this is breaking it to two is even. You can write the code, right? Breaking it to two because that is what we do in the forward passing. So in the backward passing return trip, we need to keep merging sorted data. So merging sorted data is not difficult. Not only is not difficult, not time consuming also. Of course, we are more interested in time consuming because difficult things we can handle. That is why we have software engineers. Now write those logic, right? So once it's written, we are really interested in what is the performance. So performance wise also merging to sorted arrays is not very inefficient. It's very efficient. Okay. Right. So now let's see uh, how to merge two sorted arrays. Remember now we have two sorted arrays. 2, 2, 4, 4, 8, 8. Okay. So sorting two sorted arrays is not difficult thing. Now you can see this is a sorted array. This is a sorted array. 7, 14. Every number is bigger than the left one. Right? So now can you think of a logic to merge these two into a one array? One array. Right? If you think for another 2 minutes, you will definitely come up with the algorithm. Can someone explain in simple English how are you going to sort it? How are you going to merge this into single array? There are different ways, right? Different ways you can think. Just tell me one approach that comes to your mind. Anyone? How are you going to merge this? Not sort it, right? It's already sorted. How are you going to merge this into this? Finally, it must be 7, 23, 14, 40, 39, 47, 55, 62, 74, 81, and 95. So now tell me an algorithm or logic that that is possible for us to put it into code. That means machine friendly algorithm, programmer friendly algorithm. I don't need the most efficient. Anyone has the guts, confidence about your logical thinking and your communication? That is what programmers do, right? First they think logically, so then they communicate it to the computer. So that is why we say programmers must be good at logical thinking and communication. Because we communicate it to the computer. That is why we write program.
Check the first digit from each set.
First digit from each array, okay. So then, right, we have 2, 7, and 23. What is the next step?
Then if it is small, we are taking that smaller one out of those two.
Okay, let's just give me 1 second. I will erase and so we take the first element of each array and take the smaller one, right? So smaller one is this. Then
After that, we check the remaining. No, one will remain. So
which
that one with the
now
other.
once you get the smaller one, what you do? You put it there.
Yeah.
Okay, so now we have put it there, copied it to there. Right now, what is your next step?
Now check the remaining one.
Remaining
I
one means
mean,
you need to be very precise. What is mean by remaining one? Because we have
from
now
set
three
A.
arrays, right? Which one
Set
we are
A
referring to? A, B, or C?
from A, the first element with B, second element.
First element with B, second element. Second element is this is 0, 1, 2, 3. 0, 1, 2, 3, 4, 5.
Sorry, zero element with first element.
Again, tell me.
A
You-
zeroth element with B's first element.
First element, okay, compare. Then,
Yeah, from those two taking the smallest.
okay, that is this. Then,
After again comparing A's zeroth element with B's second element.
okay, so rather than telling 8 zeroth element with B second element, now you need to write it as a logic or tell it as a logic. Because in programming, now I need a logic. How do you decide whether it's now second element and why you are still keeping the 0? So the idea is if you copy the value from this side, you need to increment that by 1 and still this remain, right? So then yes, 28. Now you copy this one. Uh, Now you increment this by 1 to come to the next one. Still you are here. So if you copy something from top one, this must be proceed to the next one. If you copy something from right or below one, that index must proceed. Now you can see we are proceeding two indexes. But if the smaller is below one, this index must be incremented. Still the other index remain the same. And if we copy from the smaller one is from the other top array, then that must be incremented because next time it will be incremented. So basically we have I and j. We compare I with I and j, ith element and jth element. Whatever the smaller value we copy and that index we need to increment by 1. Okay, so that is how you do the merging. So and ultimately you will come to the end of that. Say now assume that the 74 is now copied. Now what we are supposed to do? Now one of the array is now exhausted, but the other array's index is somewhere here. Now we don't need to compare anything because nothing to compare. Then the rest of the stuff you need to simply copy. It may be you copying from the top array or bottom array. If this come to the last, we may copy freely. Remember, this is already sorted. Or if you come to end of this one and still this one is somewhere here, then you need to just copy this. So that is your final cleanup task. And then it's merge, right? So it's a very good exercise. Create two sorted arrays and write a method that merge it into a single array. Right? I will give you the structure, but I am not going to write the code because I want you to write it. Okay? Actually, that is part of your merge sort algorithm. Okay. Uh, So you can use the recursion and see whether you can write the algorithm by yourself. It's a very good exercise because if you want to be a software engineer one day, so why you are getting salaries? Because you solve problems, right? So if you now it's something you need to develop. So why your doctor, right? Doctors get big income because they solve problems, right? And සමහරට ඉතින් හරි easy හිතෙනවා අනේ අර දොස්තරට වාහන තියෙනවා දොස්තර solve problem solve කරනවානේ මැරෙන්න යන මිනිස්සුන්ව බේර ගන්නවානේ ඉතින් ඕගොල්ලොන්ට ඒ මොනසේ වටිනාකමක් තියෙනවද කැපෙන්න යන කකුල් බේර ගන්නවා හරි මේ මනුස්සයට පට්ට වටිනාකමක් ඔයා කල්පනා මගේ වටිනාකම මොකද්ද මගේ වටිනාකම මොකද්ද සමාජයේ ඒතර කියනවා හරි මට ප්‍රොබ්ලම් සෝල්ව් කරලා දෙන්න පුළුවන් බයොලොජිකලි නෙමෙයි ලොජිකලි එතකොට ඔයාලට වටිනාකමක් තියෙනවා එතකොට කියයි ඔයාලට කියයි ආවා එන්න අපේ කම්පැනි වැඩ කරන්න ලක්ෂ 6ක් දෙන්නම් 5ක් දෙන්න ඉස්සෙල්ලම 5ක් දෙන එක ගන්න ඉස්සර දෙවන එකක් so your task is be that valuable person right so I'll just write the structure ඒකට ආස හිතුනට මදි ඒක ස්කිල් එක ඩෙවලොප් කරන්න දැන් මට ආස හිතුනට කාගේ හරි බයිපාස් එකක් කරන්න මට ගිහිල්ලා බයිපාස් කරලා එන්න බෑනේ because I don't have that skill I don't have that knowledge maybe I don't have that guts මිනිස්සෙක් heart එකක් open කරලා කපලා මේවා කරලා මේවා කරන් තරමට guts ඇත්තෙත් නැහැ ඒ වගේ දේවල් වලට right so I just write the test code you need to write the code okay later merge sort or not merge sort merge demo but you remember you merge sorted data right sorted data say I have method called merge let's return an int array say merge and I will give you two arrays okay two arrays int array uh, first int array second so your task is merge these two sorted arrays and return it okay if this has 5 data 6 data you must return an array of 11 data okay so this is not merge sorting this is the first step of understanding developing a solution for using sorting solution using merging right so I will have one array int x remember you must receive sorted array okay say 20 30 55 80 so now you don't think about merge sorting right you are thinking about merging problem so then you combine it with divide and conquer and build your merge sort algorithm it's a 10 25 Now you call, I will make it static. Then I don't need to create objects. I'll take it to a array. Result. I'll call the merge method. With my x and y. And then you print it so that you can see whether it's merged or not, right? Oh, right. So this is test code. You need to write this code. It's giving me error. Therefore, for the time being, I will say return null. Just to make it compilable. Of course, this will not return, this will give me nothing will be print, but because we are not sending array, but no errors, nothing will be there. Uh, you need to write the code. Okay, that is a good starting point. Right, null point exception because this is null. Okay, so what we get is null. That is why we got null point exception. So that is fine. But once you write the code, all these errors will be eliminated. Your output must be 10, 20, 25, 30, 50, 55, 70, 80. Okay. So let me put it into your chat. Right. So then you need algorithm when you are given an array which is not sorted, right, which is not sorted, you need to break it into two parts. Right? You break it into two parts. This is a algorithm, right? Not the Java code. You partition it into two parts and call that recursively again for the first part and for the second part. Okay, first part and second part. Right? Don't worry about this comparator. The comparator means how are you going to sort it, because it can be numbers, letters, but you can just concentrate on numbers. So then you don't need this parameter. Okay, this parameter. And then after doing the sorting in the return trip, you need to merge. Keep merging, merging, merging. So here you partition, partition, partition. And when it is two elements, you sort it and then keep merging, merging, merging in the return. In the return trip, you do the merging. Okay. In the return trip, you do the merging. Right? But it's not linear recursion. It's like a tree type of recursion. Okay. So remember we had that kind of a question in the last exam paper, also MCQ paper. Right? In the return trip again, there was further recursion. Okay. Right. So that is how, now this is the big picture. You break it, break it, break it. And rather than you coming back, we have drawn it like this, right? To keep merging. That you keep merging, merge this and this, merge this and this, and then merge this and this. And that is your final answer. So, but actually this happens in the return trip of the recursion. Right? Right. So this is the pseudocode. Right. So in the exams, they don't ask you to write Java code for this kind of complex logic, right? It's not practical. But they ask you, sometimes MCQs, they give you the sorting and ask which sorting is this. Sometimes they might ask you to write a pseudocode like this, because this is not big thing, right? So this is the merging algorithm. This is actually, you can see, I ask you to do this. You get two arrays, and in this case, the third array is also parameter. I just make it return one. That's fine. So you need to merge these two array into this, assuming these are sorted. Sorted. Okay. So you can see we have two indices. Okay. Uh, and we could keep merging from left one or right one. Then the relevant index must be incremented. Okay. So that you need to do, because remember this is recursive calls. But merging is done in the return trip. That is very important. So because you call this, then again call this. In the return trips, you keep merging, 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 merging. Okay. Right. So once you write this code, pretty much it's just calling it recursive. Okay. Calling it recursive. Right. So this is Java code. Don't worry too much about the Java code because it's somewhat complex. Yes, I know. Right. That is why they don't ask it in the exams. But uh, at least try to understand and implement this merging part. That is why I just asked you to write the merging part uh, rather than the full merge sort algorithm. Okay. But if you are interested, you can just learn, see whether you can write the full algorithm as well. But it's somewhat complicated because you need to keep breaking, 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 and then when it is just two data, you keep sort it, and in the return, you just keep merging, merging, but recursively. Okay, and so it's quite a challenging task. Okay, so therefore, I'm happy if you can, if at least write this code. Okay, but this is something you must be able to do it. Right? This is something you must be able to do it. The other thing, of course, you need a bit of thinking, time, and so on. Okay, lot of trial and error. Right. So any questions about merge sort? Because we are done. And merge sort is n log 2n algorithm. Right. N log 2n algorithm. Right. So now we'll move on to our next algorithm, quick sort. Quick sort. So quick sort is also divide and conquer type algorithm, recursive algorithm. Again n log 2n, but it's slightly better than merge sort. Faster than better means faster. Okay. Right. So sometimes learning Quicksort is a headache, right? Mainly because there are so many ways you can implement Quicksort. It's nothing to do with the Quicksort, right? Nothing wrong with Quicksort. Quicksort can be implemented in different ways. So therefore, when you go for the exam, sometimes students hate Quicksort. Okay, hate Quicksort because uh, there are so many ways it can be implemented. So then, actually, not only students, even we hate Quicksort when it comes to past paper questions and so on, because there are different implementations, different ways you can implement it. So then we don't know which one, which approach examiner is expecting. Okay. So therefore it's a bit of headache as well. Right. So I prepared another note for the quick sort. I don't know whether I shared it with you. Let me share it with you, but this only contain quick sort, okay? Because I just went through the UCSC reference book because there are so many quick sorts. So many ways we can implement it. I just wanted to get the approach mentioned in your first reference book. Okay, safe side. Okay, right. So those they say searching and sorting algorithms, it has only quick sort. Okay, because this note I have not. I try to convert this note into a PowerPoint note. Still, I have not done it. So I have only the quick sort. Okay. So therefore, just refer to this uh, for quick sort only, right? Nothing else. Let me convert it to PDF and give it to you. So you can refer to that. Okay, right. So the idea behind quicksort is again divide and conquer. Right? Divide, recur, conquer. Okay. Divide, recur, conquer. And this is the fastest and the most popular sorting algorithm uh, because this is marginally better than merge sort. So the idea is very simple, right? Implementation is also very simple. Only thing is we can implement it different ways, right? So this is the algorithm. So we select a pivot value. So pivot value can be anything. Maybe you pivot value is the first element, pivot value is the middle element, pivot value is the last element, or even pivot value is a random element. Okay, so that is why there are variations of the algorithms. Okay, because people can select pivot value in different ways. So let's assume this is your pivot value, whatever the way. So now your task is add elements below this value to left side of this. Values bigger than this into the right side of this. Right? For example, if your pivot is 30, if this is 10, you just keep it there. If this is 50, you put it to the right side because 50 is bigger than 30. You don't care where is it. It must be right side of 30. And if this is 20, you just keep it. And so on. And this side also the same. Say this is 80. It is already bigger than 30. So that is fine. But if it is something like 12, this is smaller. So this guy should not be right side of 30. So it must go to the left side of 30. So the idea is at the end, right? 30 must be in the correct position. That's a different way of thinking, right? So rather than you try to put 30 into the correct position, you arrange other elements so that 30 is in the correct position. Okay? That is a different thinking. Because if something bigger than 30 is found here, we put it to the right side. Something smaller than 30 is found here, we put it into the left side. So that we make sure that 30 is in the correct position. Okay, 30 is in the correct position. Is it clear? Is it clear? Now, is it possible? එහෙම කරන්න පුළුවන් කියලා ඔයගොල්ලෝ හිතනවාද? මම මේ කියපු ලොජික් එකේ වැරද්දක් තියෙනවා තාම.
So can you repeat again?
Now we select a number, right? And then with what we try to do is put everything smaller than that into the left of that number, everything bigger than that to the right of that number. If we can do that, then that this number is in the correct position. That is the idea. That is the idea. You can see numbers less than p, numbers greater than p after processing. At the beginning, this is just unsorted data, right? So your number is not in the correct position. Obviously, may not be in the correct position. But the idea is this. So you rearrange your data such that your pivot value is in the correct position. All the values left of that are smaller, all the values right of that are bigger. But we can't just keep that number there and do it because maybe this is not the correct position, right? So therefore, you need to arrange those numbers and pick this number to the correct position. Because this may not be the correct position for this number, right? Maybe right. So therefore, you can't just keep that number and do it. Rather, we need to keep it in a different place and do it and put it into the correct place. So that is the idea. So sometimes you may feel like this is very inefficient, but Actually, this is very efficient. Okay? Though it's not very intuitive for human mindset. Right. So as I told you, this pivot value, that is your selected value for each iteration, can be selected in different ways. Maybe you can take it as your middle one, first one, last one, or even random. Then that is why there are so many different variations of quicksort. Okay? Variations of quicksort. Right. So according to your reference book number 1, it says the best is select in the middle value. Right. So therefore we'll look at only that approach because we can't study so many scenarios. Okay. Right. So this is an example using that approach. Okay. Right. So look at this. So in this scenario example, we assume that always we take our pivot as the middle one. If it is even number of things, yes, maybe left hand side has one data less than, because there's no perfect middle, right? So this one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So therefore we have taken this one. Oh, that is fine. This is 4 element. This is 5 element. That is fine. Because we don't care whether it's perfect middle, somewhat middle, or the best middle we can find. So then we can't keep this and do it because 6 may not be in the correct position, right? Maybe ultimately 6 should go into something somewhere else. So therefore what we do is we take it to the edge. අපි අපට අයින් කරගන්න. How can we do? We can swap it with the right 10. Or you can even swap it with the left 10. Let's concentrate on one approach because that you can see there are so many ways we can do it. Let's assume we always take the middle one as the pivot and then we swap it with the rightmost element. So that means 0 comes here, 6 comes here. Okay. But this is our pivot or the reference for this iteration. So then what we do? Right. So now we have done the step number 1 and 2. Step number 3. We search from left to right, start at low. Start at low. Looking for a large element. The large element means larger than this. And we get a larger element than this pivot because now pivot has been put it into the end. We stop. Otherwise, you keep coming left, sorry, right. Right. And parallelly, we also start from right to left, right then to left, looking for a small element than this. This is your high, right? So you are looking for something smaller than this. So 7 is not smaller. So then you go to the next one. 2 is smaller. No, we stop. Now we have found something bigger than 6 into this side, something smaller than 6 from this side. Right? So then now we have stopped because we have found. Now you need to set those. 2 goes there, 8 goes there. So this is the result. Okay, this is the result. Okay. Is it clear? But this is not the end of the story. Now we are proceeding. Right, we must swap these two elements because we have found something bigger than pivot in the left, something smaller than pivot in the right. So we swap it. So as the algorithm continues, now we need to continue this algorithm. Now remember last time we were there, here and here. Okay. So last time we were there, here and here. Now you continue from here. You keep looking for smaller than 6. Sorry, bigger than 6. Not bigger, not bigger. We found a bigger than 6. And last time we were here. Now we go leftward looking for something smaller than 6 or the pivot. Yes, we found. Now again do a swapping. 5 comes here, 9 comes here. And you continue. You go there looking for something bigger than 6. You go there looking for something smaller than 6. Now, this is not something bigger than 6. This is not something bigger than 6. This is something bigger than 6. Okay. Now, you need to go other side also, looking for something smaller than 6. 3 is something smaller than 6. But by the time you have cross, you can say then a cross maybe. Then a kapagene. If it is cross, you don't need to consider that. Okay? Because that is fine. That is fine. Okay. So now we have ended up in 3 and 9, but we have cross because 9 came from left and this is we came from right. We came from right. So therefore, that is not something we supposed to accept. Okay. However, at this point, I and j have cross positions in the array. Consequently, SAP would be useless because it's useless because already this is 3 is smaller than 9. Hence, above figure shows that the item being accessed by j is already correct place and it should not move. Okay? That is the idea. So that means we stop when those two variables cross. Okay. So now the final step is we need to swap the element in position I and the element in the last cell because remember the pivot was kept in a temporary location. Temporary location. So now we need to copy this element with this so that 6 come to the correct position and 9 goes there. Now all of a sudden you can see that elements smaller than 6 is here, elements bigger than 6 is here. So that means now 6 is in the correct position. 6 is in the correct position. Got it? Now what you do? Now you do the same for this array recursively. Take the pivot as a middle, put it into the left hand and do the same logic and then that value will also be in the correct position. And then do it for the left half, right half, left half, right half. Of course, if you have thousands of data, you need to do it in recursive manner. And this side also you do it in the recursive manner. And do it for this, maybe if you have 100 data. Right? So it goes like this and every time you find a value which is in the correct position. But every time your array is getting smaller and smaller, right? It's sort of very excessive recursion happening. Okay? But there's no need for merging, right? So at the end, your array is sorted, right? So that is called quick sort algorithm. And this is just one approach. There are different ways you can implement this sorting, right? Because whatever they at the end, your pivot must be in the correct. Can you should be able to put in your pivot into the correct location. So this is just one approach. There can be some other approaches as well. Not can be, there are. If you refer to 10 people and 10 books, they sometimes talk about 10 different ways you do it. Okay. Right. So that is called quick sort. Okay. Quick sort. Any questions? And this is one implementation of the quick sort, right? So don't think that this is the implementation of quick sort. This is the one that is mentioned in your reference one. Okay. But sometimes examiners, unfortunately, I have seen some MCQs, they have referred to some other ways of selecting pivots. Still, we can't study all the different variations of quick sort, right? Right. Any questions about quick sort? And again, it's n log n algorithm, but better than merge sort. Better than merge sort. So I have given few approaches, but I don't think that you can remember all these approaches. Okay, so just concentrate on the new node. Okay, for the quick sort. But there are so many ways, but you should be able to understand the pseudocode, not the real code. Okay. So you can say if element is less than bound, right? You partition it to two subarrays, and you do it for each and every subarray you keep doing. You make sure that your pivot is in the correct position. Right? Pivot is in the correct position. Whatever the algorithm logic you can do, as long as you can put your pivot into the correct position. All the elements to the left are smaller than that. All the elements to the right are bigger than that. And you keep doing this recursively for the left hand side, then right hand side again. Left hand side and right hand side again. Okay, so you can see this is getting called like a tree, right? Like a tree. So I have given you the implementation anyway. It's work. Don't worry too much about, right? It's very complicated, fairly complicated. Right? Even I can't write this without looking at it. Okay. So don't worry if you can refer to the this note. Don't worry because this is a little bit messy. Okay. Right. So now we move on to our final sorting algorithm, uh, heap sort. Not final one. We are going to look at one more, actually two more, heap and one more. Okay. Heap sorting we have already done. Right? Remember we discussed after binary search tree, because in binary search tree data is sorted left to right. We look at what is binary heap is. So binary heap is sorted top to bottom, either the smallest to bigger or the biggest to smallest, depending on the your select choice, right? So therefore that heap data structure, we can use it as a heap sort. Actually, the main reason for heap data structure is to do heap sort. Okay. So remember your heap can be either max heap or min heap. Max heap means your top is the biggest. Remember the below you must have smaller numbers. Next level you must have smaller numbers. Say if this one, these two must be smaller than this. That's it. These two must be smaller than this. And then we have another two. These two must be smaller than this. It's not necessarily sorted this way, only sorted that way. But again, related to your parent, not related to your siblings, parents or uncles. People like uncles like parent ke cousins la. Sorry, parent ke siblings la. ඒගොල්ලොන්ට සාපේක්ෂව ඔයා පොඩි වෙන්න ඕනේ නැහැ. පේරන්ට් සාපේක්ෂව පොඩි වුණා වැඩි. And remember when we create our heap, we always make it complete, right? And this one admin go on the left to right. ඉවරනම ආයෙ මෙහෙම යන්න. යට පේලිය පිරෙන්න ඕන වමේ ඉඳලා දකුණට. හරි heap වල ඒවක් කතා කරා. We discuss that. And also we discuss how to create the heap, right? How to create the heap. Whenever we have a new data to add it, we put it into the correct position where it preserve the heap property. So then you need to do a shift up. If your data is smaller than this, you need to swap it. And again, if this is smaller than this, you need to swap it. If not, you have come to the correct position. Now it's heap property is also preserved. So first you preserve the shape property, then we preserve the heap property by swap shift ups if required. So then again it's a heap. And you add the next one again and again and again. Right? So we discussed that, right? We discussed that. Right. So just to refresh it, can you create the heap for this? Tackle heap पे खाता max heap पे खाता max heap पे खाता max heap पे खाता tackle खाता quickly do this. First, at the first one. Next, at the next one, preserving the shape property. Now 80 is more bigger than 40, therefore you need to swap it. 80 and 40. Ah, දැන් ඉතුරු ටික කරගෙන යන්න. මේ කරලා තියෙන ඒ වෙලාවේ හදන්න නැතුව එකපාර හදලා ඉවරලා හදලා මේව කරලා. හරි. That is another approach actually. The second approach. මෙයා නිකම්ම දාලා මේක 40, 80, 20, 60, 10, 50, 30, 70, 90 කියලා. That is preserving the shape property. So then it is checking and doing. So that is another approach. Or you can then and there fix it. Then and there fix it. Because at the end what we need is a heap. හරි. මෙහෙම කරනවා නම් මොකද කරන්නේ? So out of these, 90 is the bigger guy, you need to swap this. So 90 goes there, 60 goes there. මොකද ලොකු එකනට ගන්න නැත්නම් ආයි මේ පැත්තට කරන්න වෙනවා. Okay. So then you compare 90 and 10. 90 is bigger, you swap it. So 80 comes here. So then you compare 90, in parallel you need to do the right side. Right? So here 50 is bigger, you swap it. Then out of 80 and 50, 80 is bigger and 40 is smaller, so you swap it. So then you have the max heap. Right? So that is the second way of creating max heap. You just add the data filling shape property. එතකොට හැමතිස්සෙම දාන්නේ මේක 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 ඔන්න හොඳයි පිරවල. ඊට පස්සේ හදනවා. අනිත් වැඩේ තමයි ඒ වෙලාවේ හදනවා. ඒ වෙලාවේ හදනවා. So I have given you some links. Okay, I forget to mention about that. To play with these things, right? Right, I have given you some of these. You can see binary heap. Use these things, okay? So let's create a new one. So how can I start this? Is this a heap? Yes, 99, 90, and 70, 64, 75. Yeah, it's a heap. Right. Right. So let's create with only one element first. Say 30. Done with that. Right. So that is my first one. So now let's insert 60. So 60 will go as the left child. Right? Nothing to swap. Yeah, swapping is needed because 60 is bigger. So this approach is then and there you fix it. Right? That is second approach. First approach. Second approach is you just do it and then fix it. But this is the better approach actually. And now I want to add 80. Right? So 80 is added like this shape property. Now swap it. Okay. Say I want to add 40. 40 will be added as a left child of 50. Then there will be swapping needed. But that's it because 80 is bigger. Then what is there? Other 65. it will be added as a right child and swapping is needed and that's it. Nothing else. මෙයා 60 නට අවුලන්නේ. මේ පුඩත් එක්ක විතරයි compare කරන්නේ. Okay. Now what happens if you add 60 64 කාර්ද කියනවා මොකද්ද වෙන්නේ 64 add කරොත් නැත්නම් 62 add කරොත්. So 62 will be added as preserving the shape property. 62 will be added somewhere here. Then there's a comparison. 62 will come here. 60 will be here. Then when you compare these two, the bigger is 65. So therefore nothing to change. 62 will be here. Right? 62 will be here. Okay. And so on. Okay. So now swapping is done. That's it because 80 is bigger. 80 is big. Okay. Right. So now that is how you keep adding. You are adding random data, right? It's not sorted. But if you now keep taking from the top, it's already sorted. Right? It's already sorted. So that is the idea. Okay. So you can see heap sort, extract max. Now I want to extract 80. How to do that? You replace this with this one because we need to preserve the shape property. So then adjust to preserve the max heap property. Okay. So let's say extract max. What is that? Yes, extract max 1. Not extract max. So how do you call it? Okay, let's say heap sort. Extract. Okay, delete always the first one. Okay. On them max now. So this will be replaced with this. Sorry, this. Now when I again extract, delete. So this will be replaced by 40. 65 is taken. It will be replaced by 40. Then you need to adjust. That means 62 will be taken now. Okay. 62 will be taken now. First it will be replaced with 40. Okay. Then it will be adjusted with 62 because 62 is bigger. So now when you keep taking, basically it's sorted. Right? Once you put it into the heap and keep taking, actually what you are getting is the sorted data. Okay. So now this will be replacing this because we want to preserve the shape property. Then do the adjustment. Okay. So this will be replaced by 30. Then it will be replaced with 60 because 60 is the bigger. Now you can see when you keep taking, what we get is sorted data. Right? So if you want to sort something, you put it into the heap and then keep taking from the top. So then what you are getting is sorted data. So that is called heap sort. Is it clear? You just put it into the heap and you keep taking. Then and there you adjust it. Okay, because that is the better approach. Okay. Right. මෙතන අතට කරලා තියෙන හොඳම approach එක නෙමෙයි. Then and there you adjust it. Okay. And then when you keep taking from the top, it's already sorted. And this algorithm is n log 2n algorithm. Again, n log 2n algorithm, just like quick sort, merge sort, but this is not considered as efficient as quick sort. So therefore, all are n log n, but out of these, still the quick sort is considered the fastest. Okay? Right, so that is called heap sort. Is it clear? Because we have already done that, right? Right, and the final sort is radix sort. Actually, there was a past paper question in the last paper. I thought we had done radix sort. Actually, today only we are doing radix sort. I will මොන data වලටද radix sort එක හොඳ කියලා? මම කිව්වේ අර ඉලක්කම් ටිකක් තියෙනවනේ හොඳයි කියලා. නේ. මං හිතුවේ අත ප්‍රෙඩික් සෝට් එක කරලා තිබුණේ කියලා, but today only we are doing it. Sorry for that. Right now, you should be able to understand that question better after I explain radix sort. Okay, radix sort is not a major type of sort. So radix sort is used in special cases only, like set of characters, like set of few digit numbers and so on. Okay, like telephone numbers, ID card numbers. Even we can use it for sorting words, English words, and so on. Okay. Right. So the idea is, right. So the idea is, say this is our data. Okay. We'll take example. You make it all fixed with data. ඒකන්තර ID numbers වගේ මේක හොඳයි කියන්නේ. මොකද ID numbers හැමෝටම fixed with තියෙන්නේ. Telephone numbers fixed with තියෙන්නේ. If not, you need to make it fixed with. By in this case, we can prefix with zeros. Right? Prefix with zeros like this. Okay. So that is why it's ideal for fixed with things like telephone numbers, ID numbers, and so on. Okay. Right. So then the idea, then what we do is we take the rightmost thing, rightmost digit or letter. Then we put it into sort of a, now remember this sort is called radix sort. Okay. We put it into some containers. Or it can be array or stack or whatever, right? Some sort of a container. Say if it is zero, we put it into zero container because this is zero. So 0, 1, 0 is here. This is 5, we put it into the 5 container. 0, 1, 5 is put in there. This is 1, you put it into the 1 container. This is 0, you put it there. This is 5, you put it there. This is 0, you put it there. This is 5, you put it there. And this is 0, you put it there. Okay, order does not matter, right? Just you put it into the correct container. Okay, just you put it into the correct container. Some containers are empty, that is fine. Okay. So now what we do, we take it from container by container. So this is 0, 1, 0, 0, 6, 0, 1, 0, 0, 5, 0. Then 0, 0, 1, then 0, 1, 5, 0, 0, 5, 0, 2, 5. Again, this order doesn't matter, but you take it from left to right. Left to right. This container, then from this container, this container, this container, and so on. Okay. Now the idea is, now you can see the last digit, bigger values are here, smaller values are here, intermediate values are in the middle. Now it's sort of a sorted by the last digit. There can be ties, that is fine. Okay, only the last digit. You can see it's sorted by the last digit. Now what we do is again we put it in the containers, but this time we look at the next immediate right digit. Because earlier we look at the left rightmost. Now we look at the next one and you put it into the containers. So this is 1, you put it into the 1 container. This is 6, you put it into the 6 container. This is 0, you put it into the 0 container. 1, 0, and so on. And again you take it from left to right. Right? 1, 0, 0, 0, 0, 1, 0, 0, 5, and 0, 2, okay, and 0, 5, 0, 0, 6, 0. Now you can see that this is 0, 0, 0, 1, 0, 5, 1, 0, 1, 5, 2, 5, 5, 0, 6, 0. Right? On there, වමේ ඉඳලා දකුණේ ඉඳලා sort වෙලා තියෙනවා. Still it is not sorted according to the first digit. But if you look at the second and third digit, now it is sorted. Okay. Now you again put it into the containers, but now you look at the first digit. Right. දැන් මෙතන එක ටික අසාධාරණයි. ගොඩක් අය මේකට වැටලා තියෙනවා. ඒක කරන්න දෙයක් නැහැ. Right. Again you take it. Right. Again you take it. Okay. But because already it's sorted by second and first digits. Second and first digit. Right. Then now when you take it, I made a small mistake there. මේ දාන පිළිවෙල වැදගත්. හරි. දාන්න ඕනේ වමේ ඉඳලා දකුණට. So ideally this should be stack. Okay? Yeah, this should be a stack. පිළිවෙල අරගත්තා නැත්නම් ආයි අවුල් වෙනවා. Yeah, so this order is important, right? So therefore this should be stacks. Okay? Now we have put it and now we again take it, right? But no, not stack, it must be a queue. Sorry. දැම්මට පස්සේ ගන්න ඕනේ මෙතනින් 001 005 010 015 025 050 060 and then 100 මේවා ඉතින් මුකුත් නැහැ. Okay, so now of course you can remove your leading zeros because we just added to make it fix, and now you can see it's sorted, right? So we basically sorted first by the last digit, next digit until we have considered all the digits. So yeah, it's super important you put it into like this and take it like this. So this must be queues actually, not stacks. Okay, queues. And now it is sorted, right? So this is something we can use when we have this kind of a sort of a fix with, or we can make it fix with numbers. This is not good for something like 12.85, so many big variations like 2825.78. Okay, so for big variations, this is not the way to go. Okay, but when you have fixed with numbers like set of 34 numbers and so on, this is another option. Okay. Right. So that's it. Okay, so that is a very special one, right? It's not very efficient one or whatever. Just we took it last as additional one. Okay. But anyway, they asked about this, right? Last year also there was a question on that, right? Where what kind of situation radix sort can be used. Right. So now the syllabus is officially over. Right. Syllabus is officially over. So after the break, we want to finish our, we did 2024 paper 1, but we did not do 2024 paper 2. And also we need to do 2023 paper 1 and paper 2. Okay. So now let's move on to 2022 paper 2. Sorry, 2024 paper 2. Okay. Which is a very tough paper anyway. Paper 1 also was very tough paper anyway, right? So last year paper was pretty tough. Right, so the main reason is so early days they used to give a lot of sub questions, right? So now the unfair thing is you have just, right, you can see one first question, just one question. I don't know whether this is a past, because this is what they have published in the university VLE, but it has only one question, right? Maybe they had some parts and maybe they have given marks to all the students, or maybe the question was wrong, because this can't be the case, right? Just one question, that's it. And second, we have A and B. Okay. So the thing is, if you don't know something for some reason, all of a sudden you're under tremendous pressure. I'm pretty sure there should be some other parts. Maybe they have given full marks, or there were some errors in the questions and they have given full marks or something. I don't know, right? Because I have not seen the original paper. Right. Anyway, so let's do it. This is anyway a very tough question as well. Unfortunately, you can see it's a very tough question, and that's all. Right. So that is half of the second paper. Right. So let's try to do this. This is anyway very tough. I just tried that. What is the upper bound complexity of the pseudocode given below? Clearly show the intermediary steps of computation. Okay. Right. So what is the upper bound complexity? Upper bound complexity is big O notation. And big O notation. Now, if you look at the outer loop, because you need to consider the outer loop, then that into the complexity of the inner loop, because nested loop means like that. For example, if you have 4 I equal 0, I is less than 10, uh, I plus plus. And again we have 4, say j equals 0, j less than 10, j plus plus. Then you print, say I and j, I comma j or whatever, okay? So what is the complexity of this? Can someone tell me? What is the complexity of this program?
N squared.
Sorry?
Are you asking the big O notation of this?
Yeah, big connotation.
N squared.
Yeah, and this is n squared notation. Forget about n. Just give me the hard coded answer for this particular example. This is 10. This is 10. Of yours. That means your n is 10, right? So then this is 10 squared or 100. Okay. If you just try to customize it to this answer. Okay. Why is it? Because this iterate 10 times. And for each one, this iterate 10 times. So therefore 10 into 10. Oh, that is actually, that is how we say n squared also, right? N squared is the general answer. This is the specific answer. Right. If this is I to 0 to 10, and if this is 0 to, say, j is less than 5, what is the uh, performance in sort of a big O notation, but I need a hard-coded answer. This goes from 0 to 9. This goes from 0 to 5. 0 to 4. Anyone? So this iterate how many times? 10 times. For each outer iteration, how many inner iterations? 5 times. So when this iterate for the first time, there's 5 iterations of this. Second iteration, another 5 iteration. Third iteration, another 5 iteration. 10th iteration also, there's another 5 iteration. Therefore, how many total iterations? 10 into 5. 5, 5, 5, 5, 5, 10 times. That is 50 times, 50 iterations. Earlier, 100 iterations. Right? So if therefore this is going for n times and this is going for n times, n into n squared time of iterations are there. So basically this will be executed n squared time, or in this case 50 times. So you need to understand this. Okay, you need to understand this. And if you have another inner loop, that is n cube. Okay, n cube. Okay, so therefore you need to consider how many times this iterate, how many times this iterate. Okay. So what about this? So this is that kind of sort of a very, it's a good question, but fairly tough question as well. So let's say we have this kind of a scenario, because this is also, you can see two for loops, okay? Say I have this one, for in I equal 1, I is less than n, I plus plus. For int j equal 1, j is less than n, j plus plus, print, say I comma j, okay? I, then plus some space and j. So this is n by 2. Now what is the big O notation? What is the performance? This iterate for n times. And for each outer iteration, how many times inner iteration happens? N by 2 times. So here 1 to n by 2 times, 1 to n by 2 times. So that means how many times this statement will be executed? N into n by 2 times. N into, not n into n times, n into n by 2 times. Okay. Right. So now let's look at this one. Okay. Now let's look at this one. Similarly. So this is where pretty tough one actually. Now for the last 2, 3 years, examiner is very tough on this kind of big O notation questions. Okay. So that means you need to master it with a lot of exercises and so on. Okay. Right. So what about this one? What is the upper bound complexity of the pseudocode given below? That means big O notation, right? Worst case. Clearly show the intermediary steps of the computation. Now first let's look at the outer loop. Right? Outer loop. I start with 1. I is less than n. This is I into 2. So the best thing is you just write some sample values for this I value. So initially I is 1. Then I is 1 into 2, 2. Then next time, okay, forget about this. This just I'm considering the iteration. Next time, current I into 2, 4. Next time, current I into 2, 8. Next time, the current I into 2, 16, 32, 64, and so on. Okay. So n is something we can think of because n is not given, right? So n can be anything, right? N can be 100, it can be 1000, okay, and so on. So if n is say 64, say n is because this is less than. If n is 65, how many times this iterate? If n is 65, how many times this iterate? Anyone? This outer loop.
Five times?
Why? Why do you say it's 5 times? How many times this for loop iterate? N is 65.
Because it can go up to 64.
So when you go up to 64, is it 5 times? This is 1, right? When I is 1, next time I is 2. 1, 2, 3, 4, 5, 6, 7, right? How do you get 5? Is it you did not count correctly?
Sorry, sir, I didn't count
Yeah,
correctly.
you did count correctly, but right, yes. So you can see if n is 65, this can iterate 1. First time I will be 1, right? Next time I is 2, still 2 is less than 65. 4, 8, 60, 32, even 64 is there. Okay. So that means because n is a constant, right? N is a constant, right? We can just use n for our answer. But when n is 65, we can execute for 1, 2, 3, 4, 5, 6, 7 times. So next one is 128. So if n is 129, it can execute for 8 times. If it is 33, it can execute 1, 2, 3, 4, 5, 6 times. Right? If it is 17, 1, 2, 3, 4, 5 times. If it is 9, 1, 2, 3, 4 times. Now you need to see a connection between these. Okay, connection between these. Can you see a connection between these? Because if it is 4, 9, it is 4 times. Because it starts with 1, right? Start with 1. 1, next time 2, next time 4, next time 8. For example, if it is 65, this execute for 7 times. Right? පේනවද pattern එක? එකපාර පේන්නේ නැහැ. මේවයි ගණන්. මොකද අපි හැමතිස්සෙම බලන්නේ දෙකේ පාදේ, දෙකේ බල. So this is 2 to the power. Sorry, this is if you take 128. So let's take 33. What is 32? If you take 32, 32 is 2, 4, 8, 16. Right? 2 to the power 1 is 2, 2 to the power 2 is 4, 2 to the power 3 is 8, 2 to the power 4 is 16, 2 to the power 5 is 32. Okay? 2, 4, 8, 16, 32. Correct, right? 1, 2, 3, 4, 5. So 2 to the power 5 is 32. Here, 64 is 2 to the power 6. 128 is 2 to the power 7. Right? 16 is 2 to the power 4. 8 is 2 to the power 2. Okay. And then we have, if it is 5, we can take it 1, 2, 3. That is 5, we take it as
4.
Yeah, 5 we can take it as 4. That is 2 to the power 2. Right. So you can see when this is n is 3, right? When n is 3, it iterate 2 times. When n is 4, right? Sorry, when n is 9, sorry. When n is 5, it iterate 3 times. When n is 9, it iterate 4 times. When n is 17, it iterate 5 times. When n is 33, it iterate 6 times. Right? So that means this is when n, this is your n minus 1. So when this is n, it iterate 2 to the power n minus 1 times. Right? For example, sorry, it's other way, right? Other way. When n is 2 to the power n minus 1, it iterate these times, right? Right? Log 2. So therefore, this performance is log 2 performance, outer range. If for n, it is log 2n. So that is why when you have 17, how many iterations? Log 2, 4. Log 2, 4 plus 1. That plus 1 is ignorable, right? Because just 1 is, when we have a large number of n values, 7 and 8, we can consider sort of the same, right? 6 and 7, we can consider the same, right? 100, 101, compared to 100 and 101, just 1 is ignorable. So therefore, we can say that this is, when this is n, right? N, how many times iterate? Log 2n. So when your n is 65, it iterate 1, 2, 3, 4, 5, 6, 7. Because 64 is log 2 to the power 6. So therefore, number of iteration is log 2, 64. So for example, when it is 64, how many times iterate? Log 2, 64 is what? Log 2, 2 to the power 2, 4, 8, 6, 2, 4, 8, 16, 32, 64. So therefore, log 2 to 64 is 6. When it is 64, right, 64, it iterate 6 times. Actually, 7 is the real one, but you can ignore the 1. So, okay. So when it is 65, it iterate 6 times. That is log 2 64 or 65 minus 1. That minus 1 we can ignore. So therefore, this one's performance is log 2n. Compared to n, this will iterate log 2n times. Okay. So that is why when it is 65, it iterate 7 times. 7 times. When it is 129, it iterate 8 times. So 8 is close to log 229. Okay. Or rather, 129 you can consider 128. That is 7, but that plus 1 you can ignore. So therefore, remember when you have a number and 1, n plus 1 we can consider it as n. Right? Because compared to big number of n, large number of n's, uh, just adding 1 to 1000 is still we can consider 1000, right? Yes, actually it's 1001, right? So that is one of the assumption we used in big O notation. When big n values compared to n, 1 we can ignore, a constant we can ignore. Not only that, compared to n square, we can even ignore n, right? මතක නේද n square තියෙනකොට n අතාරිනවා අපි. Right? For example, this is 100 squared plus 100. So this is 10,000. 10,000, 100 කියන එක අපි 10,000 කියලා ගන්න. මෙයා වයින් කරන්න. එතකොට n plus 1 වලදී අපිට පුළුවන් 1 අයින් කරලා දාන්න n කියලා ගන්න. So therefore this is log 2n. This performance is log 2n. How many times this iterate? For n value n, log 2n. So value 17, 5 times, 65, 7 times, 129, 8 times. So therefore, this is a log 2n performance, right? Because this is multiplied by 2, okay? Is it clear? So that is only the first part, right? Outer loop. Now you need to look at for each outer loop, how many times the inner loop executes. This is like a maths question actually. It's a tough question, right? එතකොට මේ ටික ලිව්වම මට අඩු ගන්න ලකුණු කීයක් හරි එනවා දැන් log 2n කියලා ලිව්වට පස්සේ හරි because it says explain clearly show the intermediate steps, right? ඔයා පෙන්නනවා ඔයා කොහොමද මේක ගත්තේ කියලා log 2n කියලා ගත්තේ. Right. So then what about this? කියන්නේ දැන් මේක එන්නේ මෙයා වැඩි කිරීම කියලා. මොකද මේ 10යි මේක 5යි නම් 10 into 5. ඒක වගේ මේක එන්නම් මේක එන්න n into n. එහෙනම් දැන් බලන්න මේක. Right? For n. Right. So what about this? Again, try to write some sample output. So this always go from 1 to p is less than or equal to n. That same n. And this is p is p plus j. Okay, so let's say n equal 10. අපි නිකමට හිතමු n equal 10 කියලා. So initially j is 1, right? And n is always 10, right? N is a constant. අපි n කියලා ගත්තේ දැන් 10 කියලා. So then your p must be less than 10, right? Because n is 10. So my p is less than 10, right? Sorry, p is 0, right? Sorry, p is 0. So the 0 is less than 10, true. 0 is less than 10 is true. So p less than or equal to n is true. අපි එහෙම ගමුකෝ. N is always 10 and we took j1. j1 මම හරියට ලියන්නම්කෝ. So this condition says is 0 because p is 0. 0 less than or equal to n, we took n as 10. So this is true. 0 is less than or equal to true. So therefore you come into the for loop. Now you calculate the p plus j, right? So current p is 0. Current j is 1. 0 plus 1 is 1. Now your p is 1, right? P is 1. Now you go there. J is incremented. J is 2. Right? J is 2. Again, you check. Is P less than 10? Yes, P is 1. 1 is less than 10. Okay, I've made 5 iterations. Yes, 1 is less than 5. So therefore, again, you come here. Your P is P plus J. Current P is 1. 1 plus 2 is 3. So your new P is 3. Okay, your new P is 3. So then again you go there and increment J. J is 3 now. Is P less than or equal to N? N is 10, N is 5, okay? We took N as 5. So now my P is 3. 3 is less than or equal to 5. Yes, you come here. Current P is P plus J. So current P is 3 plus 3. Right? So J goes 1, 2, 3. Yeah. 0, 0 plus 1 is 1, 1 plus 2 is 3, yes. Then 3 plus 3 is, because P is 3, J is 3, 6. 6. Okay. So then you again go and increment J, 4. Right. My P is 6. Is 6 less than or equal to 5? No. So then we stop it. But if you take N as 10, then this continues. Api 10 kilagamu. So now P is 6. 6 is less than or equal to 10, yes. Now what is my current P? New P. P plus J. 6 plus 4 is 10. Okay, 6 plus 4 is 10. And then J incremented 5. P 10 is it less than or equal to N? Yes, 10 and 10, right? 10 and 10 is yes. So then again you calculate P. P plus J. 10 plus 5, 50. J is incremented 6. Is P 15 less than or equal to 10? No. So that's you don't come into the 2. Okay. Now when n equal 10, how many times we executed this? How many times we executed this? 1,
Okay.
2, 3, 4, 5, right? 5 times. 5 times, right? Now you need to see a connection between my n and how many times this iterate. How many times we iterate? Because first time my P is 0. Next iteration my P is, because how many times it iterate depends on P. And of course N. First time my P is 0. Sorry, not first time my P is 0. First time my P is 1. Because 0 plus 1. First time is after execution, okay? Inside this, my P is 0 plus 1, 1. Second times, 1 plus, now my J is, now this is my J, this is my P. When J is 1, at the end, my P is 1, because 0 plus 1. When J is 2, because J is incremented by 1, my P is 1 plus 2, 1 plus 2, which is 3. When J is 3, my P is 3 plus 3, 6. When J is 4, 10. When J is 5, 15, and so on. Okay. And I check whether my P is less than N. P is less than N. Okay. So if my N is 15, this is the last one. This is the last one. Because then my P is less than or equal to N. Next time P will be bigger than 50. Right? So therefore, if my N is 15, this is how many iterations. But if n is 30, because next time it will be 6 and 15 plus 6, 21. If n is 21, this is my last iteration. That means when n is 1, it iterate pattern. Now, there should be a hidden pattern somewhere. So we need to see connection between this is number of iteration, that is our performance, and this is your n. Okay, shall we check with ChatGPT because I can't see a pattern, unfortunately. Outer we can see, I can see, but inner I can't see. This is like IQ question, okay? So this is the code, and it doubles each time. Because it doubles each time, the inverse is log 2n. Okay. If it triples each time, inverse is log 3n. So therefore, that part is correct. That is not difficulty, right? So the outer loop, log 2n. Right. Now, what about inner loop? This is the sum of the first j numbers. 1, 2, 3, and so on. Yeah, you can see 1, 2, 3, 4, 1, 1 plus 2, 3, 3 plus 3, 6, 6 plus 4, 10, 10 plus 5, 15. Yes, it's a sum. Yeah. So ChatGPT try to see a pattern here. Okay. This is 1 plus 2. This number plus 3. That number plus 4. That number plus 5. That number plus 6. Yes. So ChatGPT try to see a pattern. So this is the sum of the jth number. Sum formula is this. So what is that? So it's a tough question. Okay. This is the sum of the first j numbers, p value. And this number must be less than n. Yes, that is our condition, right? Because this p must be less than n. That is also fine. P must be, your p must be less than or equal to n. Now, how do you get this? How do you get this? That is a problem. How do you get this?
So it is triangular number pattern term.
What do you mean by triangular number? Can you explain what you mean by triangular number? Then I can think of it.
Triangular number means if the first term is 1,
Okay.
if we add 2 to it, we will get 3. No? So first triangular number is 1.
Okay.
And second triangular number is 3.
Okay. Next one.
So for 3, if we add 3, we will get 6.
Okay.
So the third triangular number is 6.
10.
Yeah.
Then how
So
do you
if
get
J is
this?
1, if J is 1,
That means if j is 1, you add j
yeah,
plus 1.
yeah, then 1 into 2, 2. 2 divided by 2 is 1. Then it is the first triangular number.
Okay.
So if J is 2, Then 2 into 3 is 6. 6 divided by 2, 3. 3 is the second triangle number. Likewise.
So that means then say this is which triangular number? This is fourth one.
Yeah. And 4 into 5 divided by 2, 10.
4 in, now the next one is 6. 10 plus 6 is 16, right? How do you get 16? 10 into
No, sir, not like that.
10. So this is 5, right?
Yeah.
10 plus 5, 15. Now how do you get 15?
So if J is 5,
Now how do you get 15 hard-coded value?
yeah, 5 into 6 divided by 2.
5 into 6 divided by 2 is 15. Ah, yes, that pattern is there, right? Yeah, so it looks like that pattern is there. So j into j plus 1 divided by 2. Okay. Yeah, so that pattern is there. But that is a very special type of a sequence, right? Can't we see it like a normal uh, arithmetic sequence? 1, 3, 1, 3, 6. Ah, yes, we can think like that also. If you have this sequence, that is, you can see, yeah. So if you take this sequence, 1 plus 2 plus 3 plus 4 plus 5 plus 6, right? So this is arithmetic sequence, right? Rather than, okay, that definition is also correct, but this is a easier way to look at it, right? So if you take a arithmetic sequence, 1 plus 2 plus 3 plus 4 plus 5 plus 6 and so on, remember our number is the previous value plus the next one. All the previous value plus the next one. All the previous value plus the next one. And your I is incremented by 1. So this is your I is 0, I is 1, I is 2, I is 3, I is 4, I is 5 and so on. Okay. So sorry, this is 1. So it's not 0. We can start with even 1. I or j. In our case it's j. J is 1, j is 2, j is 3, j is 4, j is 5, 6 and so on. Okay. So your number will be 1, then 1 plus 2, then 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4 and so on. Okay. So therefore, it's a arithmetic sequence. Basically, it's this arithmetic sequence. Right. So there we can get the sum as Sn equal n divided by 2 times a plus z, right? First number, last number. Okay. I don't think we can do it. I think we need to think like that kind of thing, right? So this number is this plus the next that plus one divide. Yeah, I think we need to think like that. But this sequence is also there, but I don't know how to relate this. Okay, ChatGPT has taken from this sequence actually. From
So
here,
we
how
get
do
the
you?
triangle numbers by adding like that
No,
also.
now forget about the triangle number. Can't we get it from here? Because ChatGPT argue from this sequence. Right. I think ChatGPT consider this as a arithmetic sequence. Anyway, triangular number is correct because that is a very special sequence, right? Uh, I try to get it from the general approach, okay? Because triangular numbers are very special kind of a series, no? Uh, so from there, how do you get this? Should be from this one, right? Ah, yes, this formula. Say now you have j number of items. J number of items. So therefore n is j. Right? N is j. First number is 1. Last number is j. So therefore the sum is your p is your sum because we are keep summing. Remember here we keep summing. Right? Here we keep summing. Right? P is your keep summing your j. So therefore if you use n divided by a plus l, right? A divided by Sn is n divided by 2 into a plus l. N is j because we have j number of iterations divided by 2. Your a is 1 because you initialize with 1, j initialize with 1 and it goes up to j. So therefore your first term is 1, last term is j. So therefore your p is the sum up to that point. So therefore we use Sn equal n divided by 2a plus l where n is j, a is 1, j, your l is also j because this is d is 1. And this must be your p, right? This must be your p and your p must be greater than or equal to n. And so this must be, right? So therefore, this must be greater than or equal to n. Sorry, greater than n. It's a tough question anyway. This must be greater than n. So we need to find j from n now, not n, right? J we need to isolate. That we need to write in terms of n. So this you can, this is j and j plus 1. If you forget about the plus 1 part because it's ignorable compared to big J values, so this will be j squared divided by 2 greater than n. So this means j squared must be greater than 2n. So therefore j must be greater than root 2n, root 2 root 10. And compared to root 10, very big n numbers, root 2 you can ignore because this is 1.4 something. So therefore your j must be greater than root 10. So therefore this is a root 10 algorithm. Anyway, it's a very tough question. Okay. Right. So that is how they have I don't know, ChatGPT has taken it like that. Okay. So therefore ChatGPT say it's a O root 10 algorithm. So why O root 10? Because this must be greater than n. So we can ignore this plus 1 for big J values because big O notation is for big large values. That is j squared divided by 2 less greater than n. That means j squared is greater than 2n. That means j must be greater than root 2 root 10. And if you ignore root 2 because it's 1 point something, j must be greater than root 10. So therefore its upper bound is root 10. Now you have the upper outer loops log 2n, inner loop root 10. So therefore the final answer is outer big O notation value into inner big O notation because it's a nested loop. That is log 2n into root 10. Log 2n comes from the outer loop, root 10 coming from the inner loop. Okay. So that is a tough question anyway. Okay. So therefore the final answer they have taken it as root 10 log n. Log n is the inner loop, outer loop, root 10 is the inner loop. Okay. Right. So I will try to find one or two this kind of a question, right? Maybe little bit simpler question and try to do those in another session. Okay. Maybe while doing the past papers. Okay. But anyway, it's tough question. Okay. It's sort of maths question. Okay. Right. So unfortunately, that's all for the first question also, right? If you can't do that question, you lose all the marks. Okay. That is very unfair also. Let's uh, for inner loop, the loop condition is based on outside variable p, As such, P increases by 1 for each loop iteration. Therefore, uh, yeah, this is the arithmetic sequence 0, 1, 2, 3. So, value of k would be computed as square root of n. So, examiner has not mentioned how to get it, okay? It seemed to say square root of n, but actually that is the logic behind that. Similarly, the outer loop of the loop increases as powers. That is fine. So outer loop, you should be able to understand 2 to the power k. Reverse is log 2. From there, you get the log 2n. This whole one is then log 2n into square root of n. Right? Log 2n into square root of n. Anyway, examiner has not explained, but ChatGPT explained a little bit better, actually fairly good way. But anyway, it's tough question, okay? Tough question. Right, so let's get anyway. That's all for the first question. I don't know. Maybe they had added some questions, some more questions, and they have removed those or whatever. Maybe full marks given for those questions because there can't be just one question, right? I don't know. Second one, again you have two parts. The first part is straightforward, but the second part is the DSW algorithm. But I checked with your syllabus. Actually, your syllabus has mentioned DSW algorithm. Okay. So we did only AVL algorithm, but then I found that DSW algorithm is also mentioned in your syllabus. So therefore, this I can't say this is outside syllabus. That is why I gave you an updated note adding DSW algorithm also. So then you don't need to worry. We have then right. Right. Anyway, I'll explain what is DSW algorithm. But the first one, of course, you can do it, right? Uh, just add it to the binary search tree so that anyone can do it, right? Right. So that 20 marks, but here you get 30 marks, okay? Right. So first, I will explain DSW algorithm. If you have not understood it yet, anyway, I shared you the note under tree, okay? I put it in the WhatsApp group and also I uploaded to the Google Classroom as a latest note. So under balanced binary search tree, we discuss only AVL tree. Okay? So let's get back to this. Right. So the idea behind balanced binary tree is what we don't want to let some branches extended excessively compared to others. Because the idea behind binary search is using binary tree, you just go through the one particular path downwards. So therefore, if you have very long path, that means your uh, efficiency is less. So that is why we need to then and there balance it so that we have lesser number of levels, right? So this balancing can be done in two different ways. First approach is local balancing. That means then and there when you add a node, we check whether it's not balanced and fix it, right? So then and there, whenever you insert a value or delete a value, you check the balance and fix it. That is the actually easier approach. Okay. So that is what we do in AVL tree. Right. Remember, I'm not going to do it again AVL tree because we have discussed it. Right. After each insertion, if it is unbalanced, we fix it. So that is called local tree balancing. So the other approach is global tree balancing, where you fully create the tree. You don't care about it must be binary search tree, but you don't care about balancing. Right? So that is what your question is, right? You examiners ask you to just put it into a binary search tree. Now, after creating the binary search tree, we can start balancing it. So that is called global tree balancing. Right? So one such algorithm is DSW algorithm. DSW stand for some people's name, I think. Right? And there's advantage of DSW algorithm, that is it will make it not only balance, it results in a complete tree also. So complete tree means balance and the last elements are added from left to right. In the last level, elements are added from left to right. That is called complete tree. So therefore, it will result in both balance and complete binary search tree. That is anyway added advantage. Okay. Right. So ABLT we discuss, right? So the what is left rotation, what is right rotation, what is left left scenario, left right scenario, right right scenario, right left scenario, where when to use single rotation, when to use double rotation. Right. So these rotations are applicable for DSW algorithm as well, right? So that means the left rotation and right rotation. So you must know how to do the left rotation. You must know how to do the right rotation. If you are not very sure, you need to refer to the recording. Okay, right. So this is how DSW algorithm work. First, you build your binary search tree, right? If you have 100 nodes, you add 100. Now it can be unbalanced so many places because you just create it, okay, without considering balance. Okay, right now what we do in DSW approach, it's a two-step process. It's a two-step process. First, we need to convert your binary search tree into a backbone or vine. That means it will be at the end of the first step, you will get something like a linked list from your binary search tree, which is unbalanced, not balanced. You convert it to something like this. Actually, it's a binary, so it's a linked list. But you can't just create a random linked list. You need to build it using this binary search tree. So that means every node has right child only. Right? Every node has right child only. So that is the step number one, and we call it we create the backbone, no vine. So then you need to balance the backbone using certain rotations. So then you will end up with a balance and also complete binary search tree. Okay. So though it looks complex, it's actually not very complex. Actually, this is easier than the previous step also, because previous step you have single rotation, double rotation, and so on. Right. So the step number one, creating the backbone or the vine. Okay. So that means it's a right skewed linked list. That means every node has only a right child. So therefore it's actually ended up like a linked list. So how to do this? Uh, you keep performing right rotations so that every node has only one right child. So you need to start from the root and rotate only nodes having left subtrees. That's it. So you start from the root and keep doing the right rotations, but you do a right rotation only if that node has a left subtree. It's very easy. Okay, very easy. Just start from the root and keep doing the right rotations, but you do right rotations if the particular node has left subtree. That is how you do create your backbone or the vine. Okay? Backbone or the vine. So let's take an example. Assume this is your binary search tree. You have never tried to balance it. It's a binary search tree. You can see 2, 4, 5, 7, 8, 9, 12, 17. It's sorted from left to right. Okay. So now you need to start creating your vine or backbone. How to do that? Start from the root, do right rotations if that node has a left child. Now you can see this root has a left child, right? So if your root has a left child, you need to do a rotation in the root. Now you know how to do the rotation, right? Right rotation. 8 will come up, 12 will go there. The right child of 8 will be the left child of 12. ඒවා අපි කරලා තියෙන ඒ දවස්වල, right? So therefore, uh, 8 goes there, 12 goes down, with 12, 18 also go there. Okay. අපි ඊට පස්සේ අපේ question එක වෙනම කරමු. ඉස්සර කරන විදිය බලා ගන්න. Right? And 8 goes up and the right child of 11 will be the left child of 12. Okay. So now we have done the first rotation. Now again, look at your root. Your root has a left child. So that means again you need to do a rotation on the root. My rotation when you root again. Okay. So therefore 8 will go down, 5 will go up, and 7 will be the left child of 8. Right? And again you can see your root has a left child. So that means again you need to do a rotation. 4 will go up, 5 will go down, that's it. Right? And 2 will be hanging in the left side still. Okay. And still your root has a left child, so therefore you need to do a rotation. 2 will go up, 4 will go down. Right? Right? Now remember, you need to do this for each and every node. But you start from root. Now you go down. Now this is fine, no left child. No left child. No left child. Here we have a left child. Again do a right rotation. 7 will go up, 8 will go down, then lazy. Right? 7 will go up, 8 will go down. Right? 8 will go down. Then this one has a left child. Rotate. 11 will go up, 12 will go down. Still 18 has a left child. 17 will go up, 18 will go down. Now we are done with step number 1. We have the vine or the backbone. Okay. So you can see it's not difficult. Right? It's not difficult if you know the logic. Right. So now we are into the step number 2. It's a 2-step process. Now here we only did the right rotations for those element nodes having left child, but you need to start from top for the root. ඇත්තටම root එක කරකිලා කරකිලා ඉඳලා ඊට පස්සේ යටට එන්න පටන් ගන්නවා. හරි. Right. Step number 2. ඒක චුට්ටක් කල්පනාවෙන් කරන්න ඕනේ. Right. Number of nodes for perfect complete binary tree. This is theory part, okay? So perfect complete means what? It's something like this is perfectly complete. Perfect and complete. So this is the next perfect complete subtree. හරි ඒ කියන්නේ හැම එක්කෙනෙක්ටම එක්ක childrenලා දෙන්නෙක් ඉන්නවා නැත්නම් no children. Fully complete වෙලා තියෙන්නේ perfect වෙලා තියෙන්නේ ඔක්කොම ආයි මේ වගේ මෙහෙම වුණොත් perfect නෑ. Right? It must be perfect complete. So therefore if you have 3 nodes, okay, if you have level 1, you have only 1 node. Level 2 perfect binary tree has 3 nodes. Level 3 perfect binary tree has 1, 2, 3, 4, 5, 6, 7 nodes. So likewise level 4 will be having another 2, another 2, another 2, another 2. That means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And 15 will be 2 to the power 4 minus 1, 16 minus 1. And there's a pattern. If you have one level, you have 2 to the power 1 minus 1 nodes to create a perfect complete binary tree. If you have 2 levels, you need 2 to the power 2 minus 1 nodes. That is these 3 nodes. If you have level 3 perfect binary tree, you need 2 to the power 3 minus 1 or 7 nodes. Okay, 7 nodes. So therefore, if you have n levels, to create a perfect complete binary tree, you need 2 to the power n minus 1 minus 1. This is 2 to the power n minus 1 minus 1 number of nodes. Okay, so that we are going to use. Right, in our case, we have n 9 nodes. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So therefore, 9 is not, now you need to find this using this calculation, how many levels are we going to have? So 9 is bigger than 7, but not bigger than 2 to the power 4 minus 1. Because this is 50. Okay. So therefore, we are going to have, because we have 9 nodes, we are going to have level 4. Level 3 is consuming 7 nodes, but we are going to have 2 more nodes in the last level. And we are not going to get a perfect balanced binary because we are going to have 2 more nodes like this. So then 7 plus 2 is 9. Okay. Right. ඒක formula එක මතක කරගත්ත එවෙලේ හදාගන්න පුළුවන්. Right. So this is our step 2. First, perform left rotation on the odd nodes. Odd nodes, ඒ කියන්නේ මෙහෙම ඇවිල්ලා තියෙන්නේ. Right. Odd nodes. 1, 3, එහෙම තියෙන nodes, sorry. But you do only left rotations on the odd nodes starting from root until extra node count times. Now remember, in our case, the extra node is 2 because our case we have 9. For perfect binary tree, you need 7. So that means we are going to have 2 extra nodes hanging like this. So that is how you decide how many times you do those performances. Basically, we are going to do those 2 rotations to create these nodes. Okay. So that is your first thing. And that is not difficult once you understand theory. So that is the first part of the step 2. The second part of the step 2 is then again left rotate all the odd nodes starting from root until tree is balanced. So then you are done. In second step, we do only left rotations. In step 1, we did only right rotations. Okay, now we are going to do only left rotations. Okay. But remember the first step, we do it on the odd nodes. Okay. And here also we do it on the odd nodes. ඒකන මේ කියන තරම් අමාරුත් නෑ වට. හරිනම් වට තියෙන odd nodes වල left rotate කරගෙන එන්න ආගේ tree එක හැදෙන්න එච්චරයි. එහෙම හිතුවත් ඇති ආ. මේ theory ඔක්කොම මතක කරලා second step එකේ. හරි. Right. So now let's
Sir,
do it.
why do we choose odd nodes?
Because this is a technique, right? So this is 3 people get together and found a method, right? So this method is to create the perfect binary, not perfect, a balanced binary search tree. When we do like that, it happened to be a balanced binary search tree. So therefore, different people came up with different techniques like AVL, red, black, this one. So these are different techniques. Okay, different techniques. Right. So therefore, this is not difficult to remember. Basically, you mark your odd nodes and keep doing your rotations, right? Left rotations, right? But you do it from top to bottom, right? Top to bottom. Right. So let's do the first left rotation, which is based on this particular point. Okay, this particular point. So 4 will go up, 2 will go down. That is our first rotation, right? 2 will go down, 4 will go up. So then our next odd notation is we have already marked 5. Now 5 is here, right? 5 is here. Now again do a left rotation on this, not here, because this is your second mark. So when you do rotation here, 5 will go down, 7 will go up. Very simple, right? Now you can see the earlier mark nodes are here now. That is fine. That is fine. So now the first part is done because we have done the 2 rotations on nodes. Okay. Right. So now we can do the second part. Right. මේ calculation එක නොකර කරත් ඔයාලට අවුලක් නෑ. හරි. Now again, remember now we have 2 and 5 we have done. Right. 2 and 5 we are done. Now again mark the odd things in the new one. Then when I අලුත් එකේ mark කරන්න ඕන odd location, that is 4, 8, 12 and so on. So then again left rotate all the odd nodes that is in your new structure, starting from root until tree is balanced. You just do it until tree is balanced. Yes.
In the first step, why did we take only 2 odd nodes and rotate?
Sorry?
In the first step, we rotated only 2 odd nodes. No?
Yeah.
Why did it take only 2?
Yeah, that is what I explained here, right? So we have at the end, we have how many nodes? 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So when it comes to 9 nodes, what is the nearest perfect binary tree? This is 1, this is 3, this is next perfect one. How many nodes? 1, 2, 3, 4, 5, 6, 7. Right? So then next perfect binary tree will have another 2, another 2, another 2, another 2, right? Like this. So this is how it goes. Now our one has 9. So that means this is our biggest perfect binary search tree. 1, 2, 3, 4, 5, 6, 7. So therefore you subtract 7. So that means we are going to have 2 more extra nodes. So that is why we decided we are going to do initially 2 rotations. Like basically we want to get these two nodes. We want to get these 2 nodes. That is why initially we mark 2 odd locations and the 2 rotations. Because we know that we are not going to get a perfect binary search tree. We are going to get 2 extra nodes at the last level. So that is why we did. So you need to calculate that using how many nodes you are having, how many nodes a perfect binary search tree have. So 1, 3, 9, sorry, 7. So our one has 9. So therefore 9 minus 7 is 2. If our number is something like 20, then we say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Because 20 minus 15, we are going to do 5 rotations. Because we can go to the next level of binary search tree. So therefore, if originally we had only 5, 20, we are going to do 5 rotations because next bigger one has perfect one has 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. If you can't calculate like that, use the word 2 to the power n minus 1 minus 1. So then when n is 1, this is 1. When n is 2, 2 minus 1 is 1, 4 plus 1, 4 minus 1, 4. That is this. Sorry, when n is 2, 2 minus 1 is 2 minus 1 is 1, 2 to the power 1 is 2, 2 plus 2 minus, sorry, when n is 2, 2 minus 1 is, sorry, when n is 3, 3 minus 1 is 2, that is 4, 4 minus 1 is 3, right? So next one is n is 4, 2 to the power 3 minus 1, that is 8 minus 1, 7. The time is 7 now. ඊළඟට එන්නේ 2 to the power 4 minus 1, 2 to the power 5 minus 1 and so on. So your count must be some bigger than that value, but not bigger than the next value because then you can go to the next value. Okay. So that is why we did 2 rotations. Because we have 9, we know that the next smaller perfect binary tree has 7. So therefore 9 minus 7 is 2. Okay. You can see I have mentioned that max perfect binary tree count is 7. We have 9. So 9 minus 7 is 2 because we can't go for 2 to the power 4 minus 1 because that is bigger than 7. That is bigger than 9. Okay. Right. So now we have done those 2 rotations. Now what you're supposed to do is you just keep rotating odd values until you get your balance tree. Okay. එහෙම නැත්නම් අර පොඩි calculation එකක් කියලා තියෙනවා එතනින් නවත්තන්න පුළුවන් but you don't need to worry about this. Okay. So now you keep rotating, left rotating again your new word nodes until you get the balance tree. Okay, right. So let's first do the left rotation on 4. 4. So 7 will go up, and the left child of 5 will be the right child of 4. You know that, right? So that means now we have done one rotation. You know that still this is not balanced. Now you need to do the rotation on 8. So this is next node. Now 8 is, sorry, now 8 is here. Right, now 8 is here. You do a rotation. 11 will go up, 8 will go down. Okay. Now you need to do the rotation on 12 because still this is not balanced. Right, 17 will go up, 12 will go down, 12 will go down. Right, so now we need to do the rotation on 12, right? Done. Okay. Right, so now we have get into this level, right? This level. Now again you need to mark your values and do a rotation because now we have reached the end. We have reached the end, okay? Reached the end. And now it is like this. Now again you need to do a rotation from here. Okay. So now you are going to do the rotation from here. 11 will go up, 7 will go down, and the right side of 8 will be the left side of 7. And now we are done. We got a balance and complete binary search tree. Okay, now if you are wondering where do we stop, right? Where do we stop here? Or how many rotations we do here in the first level, first stage? That is number of rotation required is now we have 7 nodes. 1, 2, 3, 4, 5, 6, 7. That do divide by 2 integer division. Right, so අපි ඉස්සර කතා කරන්නේ මේ දෙපාරක් rotate කරනවා ඒ දෙක හරියද? Now count how many nodes are there in your current while and divide by 2 but integer division. So that number of rotations you need to do now. That is why we did 3 rotations, right? 3 rotations. And now again, the remainder of that. Okay, so 3 is the result from the previous integer division. Previous integer division, we got 3. And we have done 3 rotations. Now again, it do integer division by 2. That previous result, which is 1. So that means now again you need to do one rotation. One rotation from here. That results because anyway, nothing to delete. Again, if you divide by 2, again you get 0, right? So therefore, that should be the end. You do keep doing like that. So how do you get this 3? Because that 3 is the result of previous integer division. So 7 is, after doing those 2 extra rotations, how many nodes are there? So that is how you get 7. 7 is the perfect tree node count for this problem. Or this is basically the perfect tree node count. Or that is anyway, that is your this count as well. Okay. Right. So that is how you keep doing. So this 3 is used. This 3 means we need to, after these rotations, we need to do another rotation because 3 divided by 2 will be 1. But once you get to 1, that means you don't need further rotations. This is going to be your last rotation. Okay. Right. So this is your 2024 paper. Okay, 2024 paper. So it says first insert it. The good thing is it's a very small tree, therefore it's manageable. So shall we do it? Right? Shall we do it? So just use it to insert it to. Shall we take something else? But this is very. Right? It says 50, 40, 70. 50, 40, 70, 60, 100, 80, 90. Right? So we create a binary search tree, but we don't balance it because it says just add it to a binary search tree. Okay. Clearly show the intermediate steps, right? But I will just draw only one tree, but you need to show each step. Okay. 50, 40, 70, 60, 100, 80, 90. Okay. So that is, but you need to show it step by step. Okay. Right. So that is your step number one, right? 40, 50, 70, 80, 100, 80, 90, right? So now second part, generate a balance tree from the resulting tree, right? Resulting tree. So therefore you can't use AVL. In part 2A above using the DSW algorithm. Clearly show the intermediate steps and relevant calculations. So what is your first step? You need to create the why know the backbone, right? Why know the backbone? How to create the why know the backbone? So create by repeatedly performing right rotation so that every node has only right child. Start from the root and rotate only nodes having left subtrees. Right? Left subtrees තියෙනවා විතරයි rotate කරන්නේ. හැබැයි කරන්නේ මොනවද? Right rotations. Okay? Start from root. Start from root. So therefore now we can do a rotation on this root because root has a left subtree. Okay? Left subtree. So 40 will go up. 40, 50, 70, 80, 100. Okay, where's this 80 again? Myself.
So I think it's 60.
Yeah, it must be 60. 50, 40, 70, 60. Yeah, this must be 60. And this is 80. Okay. Right. So after the rotation, 40 goes up. 40 goes up. And 50 goes down. So that is our result. Now there's another left subtree. Now you need to go down because this side is okay. Now you go down. There's a left subtree. Do a right rotation. And you need to show this, right? Each and every step you need to show. So that means 60 will go up, 40, 50, 60, 70, 100, 80. Now there's another left subtree node. Sorry?
You have missed 90.
We had 90 also. Sorry. We had 90. 80 and 90, right? 80 and 90. Okay. 80 and 90. So therefore we have 90. Okay. Right. So now this is another left subtree is there. So therefore we need to do another rotation. Another rotation. So that should result in 40, 40, 50, 60, 70, 80 will go up. Okay, so then 90 will be the left child of 100 because this right child must be a left child of 100 now. 800 and 90 will be here because you need to pass it to the 8 other guy because you have a right child. Right. So now we have another left child. So therefore, again, we need to do a right rotation. So the result is 40, 50, 60, 70, 80, 90, 100. 100. That is the end of the step number 1. Is it clear? Right. So that is the end of step number 1. Right. So this is the end of step number 1. You will get 40, 50, 60, 70, 80, 90, 100. Okay. Right. So let's take that and delete everything because I need more space now. 40 to 100. 40, 50, 60, 70, 80, 90, 100. Okay. 40 to 100. Why don't I delete? Again, let the name. Let me take it back. 40 to 100. And we have the backbone now. 40, 50, 60, 70, 80, 90, 100. Now, if it is perfect tree, we are going to have 3. How many nodes we have? 1, 2, 3, 4, 5, 6, 7. Okay. Next is like this. That is 1, 3, 7. Right. So that means our one is perfectly matching to that. You can see 1, then 3, 4, 5, 6, 7. We also have 1, 2, 3, 4, 5, 6, 7. That means you don't need to do that extra rotations because our one is going to be a perfect binary search tree. Because we have 7, the 2 to the power k minus 1 minus 1, right? Is also 7. If k is 3, 2 to the power 3 minus 1 minus 1, 2 to the power 2 minus 1. Sorry. When k is 1, 2, 3, sorry, 2 to the power k minus 1, right? Is it 2 to the power k minus 1? No, 2 to the power k. Yeah, 2 to the power k minus 1. So 2 to the power 3 is 4, 4 minus 1 is, sorry, 2 to the power 3 is 8, 8 minus 1 is 7. So therefore, no extra rotations required. No extra rotation required. We just need to do our files. You can go to the step 2, part 2. No extra rotations, okay? Right. So what the step 2, part 2 says? Now we are going to do only left rotations. Left rotations. How many times? Now you don't need to do this step because you don't get extra rotations. Okay. Perfect tree not count for this divided by 2. Integer divided by 2 times you need to do it, right? So this in our case it is 7. 1, 2, 3, 4, 5, 6, 7, right? Because we never had to do the extra rotation. So 7 minus 7 integer divided by 2 times we need to do that. 7 integer division divided by 2 times, that is 3. Right? So these are the notation odd ones. So we are going to do 3 times. Then we are going to do another 1 times, that is 3 divided by 2, which is 1, right? But first we need to do the 3 times. 1, 2, 3. because we have 7 perfect nodes, right? So therefore, let's do first rotation. 40 will come here, 50, 60, 70, 80, 90, 100. So then the second one, rotate on this 50, 40, then 70 goes up, 60 goes down, then these guys hang, right? So then that is 60. So we have 80 also. Now we are going to do one more. That is 50, 40, 70, 60, and 90 goes up, 80, 100. Now we have done this 3 times. 40, 50, 60, and 80. Now we have 3, right? Now again 3 divided by 2, 1. That means we need to do 1 more times. So then that, because 1 divided by 2 is 0. You need to keep doing this if you have very large number of things, right? So that means we are going to do it here. Because this is again you mark from here. And remember, we only do left rotation in step 2. Okay. So that means we are going to have 70 up, 50 goes down, 40 goes down. So then the right child of 60 must be the left child of 50. You need to pass it. Okay. So then these guys will just come up 90, 80, 100. And now you got perfect. Yes, we know that we got perfect.
So
Because
how did you get 3 divide by 2?
now always we divide by 2.
Yeah, how did you get 3?
So 7 divided by 2 is 3.
I mean the next one, sir.
Whatever this answer is, this answer.
Okay.
Okay, so that is why I have marked it in my PowerPoint notation in yellow. I know that you are going to get this question, right? Not you, everyone. So that is why I marked here. So this 3 is this 3. Okay. 3 is the result from the previous integer division. Right? Previous integer. Now, if this is bigger than 1, you are going to do again. If this value is say 3, again you are going to do. So for example, if this value is say 5, they are 5 divided by 2, which is 3. Then again 3 divided by 2. Right? Until you get 1 or 0 here, you need to keep doing this. That means you are going to do round 3, round 4, and so on. Okay, right. So that's it. Now we have the balanced tree, and it happened to be a perfect tree as well, because we have number of elements which is part 2 to the power n minus 1. So this is our final one. It's binary search tree sorted from left to right, as well as it's balanced, perfectly balanced in this case. And that is the result. Okay. So if you look at the past paper answer sheet, so this is the result. You can see it's correct, right? 40, 50, 60,
So
70.
in exam, should you show all these steps like this or
Yeah, you
the
are
final?
supposed to show. This is the examiner is just showing the final answer, but examiner clearly say show all the steps, right? Show all
Okay.
the steps. That means you need to show like this. If I show you some old past papers, examiner show all these steps, but now this examiner doesn't show it because he's lazy to put it in your answer sheet. But yeah, that is the expectation. Okay, you are supposed to show each and every step, even when you are creating the binary search tree. Otherwise, you will not get marks. මොකද ළඟ ඉන්න එක්කෙනාගෙන් බලලා ඇන්දයි කියලා එතකොට examiner හිතන්න ඉඩ තියෙනවා. Right. Right, so that's about 2024 paper. Pretty tough paper, right? pretty tough paper. But of course, if you know DSW algorithm, that is not a tough as well as, but definitely the first question is very tough. Okay. Right. So now we have done 2024 to both the papers. Okay, both the papers. Right. So we'll take a small break and start doing 2023 paper one. Okay. Because then you are in a very good position to continue with your data structures and algorithm past papers. Okay. Right. So now it's 11:20. We'll start at 11:30. Right. Question number one. Let's see multiple answers. Yes, one or more correct answers. Negative marks apply. Which of the following statements is are correct regarding data structures? One, arrays are heterogeneous data structures. Arrays are homogeneous, right? In Java, only one type of data you can keep, so therefore A is wrong. Each data element type in a homogeneous data structure is the same. Yes, if it is homogeneous, it's the same. That is why we call it homogeneous. Now you can see this question, almost similar question was there in 2024, right? So that is the advantage of doing past papers. Data elements are attached hierarchically in a linear data structure. Of course, if it is linear data structure, there is no hierarchy. Dynamic data structures consist of fixed permanent structure. No, if it is fixed permanent, it is static. Static data structures have fixed format and size. Yes, that is why we call it static. Arrays are static. Okay. Linked lists are not static because it has dynamic size. Okay. B and E. B and E. Yes, B and E. Okay. Right. Second one. When implementing a circular queue with one array of max size minus one, it become full when. Right. So let's draw a circular queue. And it has size, max size. So this is 0, 1, 2, 3, 4. Say this is max size minus 1. Max size is 5. Sorry, 6 means this is 5. Okay. So this is max size minus 1. If max size is 6, max size is 6, 1, 2, 3, 4, 5. Max size means maximum number of elements you can add. To a circular cube, maximum number of elements we can add is 6. Size of the array. Right. And remember when we added data, so this will become your front end, right? Front and also rear. Say first you add 10, then you add 20, then you add 30. Now this is your rear, this is your front. Because when D cube, first you need to take it from there. Like 40, 50, and this is your rear, right? And when you D cube, your front will also come here. Say this is taken now. Say this is taken. This is also taken. So then this is your front. So just now let's look at the answers. Right. When implementing a circular queue with an array size, max size it become full. Now, this is when it has become full. Right? It has become full means either one possibility is your rear is here, max front is here. That means you have not taken anything. Other possibility is uh, so from rear you are adding, from front you are taking, right? So that means your rear has, you have had data, and data and data. That means your rear is here and front is here. That means you have added, say, 40, 50, 60, again 70, again 80. Now your rear has come here. Front is still here. So that means now you can't add, right? Because, right, front is rear plus 1. Front is rear plus 1. Rear plus 1. Correct, right? Because now your rear is here, front is here. Right? Because these things were DQ'd and now we have only added. Now you can see this is exactly this kind of situation. Now your rear is here, front is here. Right? Rear is here, front is here. So that means your front is rear plus 1. Right? Rear plus 1. So that means now you can't add. Actually, we don't check that like that. In reality, we keep the max count, right? That is the easier thing, but the examiner is really making it complicated our life. But anyway, this logic is correct. Now you can say rear front is rear plus 1 means you can't add it further. Okay. Front is rear minus 1. No, front must be rear plus 1. Right? Rear is front plus 1. No, rear is front minus 1. Or front is rear plus 1. But easier thing is use of this max size. Okay. Right, next one. Front is 0 and rear is max size minus 1. So front is here. That means this is a special case. This is the special case. Front is here. Because that means no, you have not deleted any DQ anything. And rear is max size minus 1. So remember max, that means your rear is here. Yeah, that is another full situation. That means still you have not overlap or you nothing has been DQ'd. So that otherwise front rear can come back here. But rear cannot come back here because front is still 0. That means you have not DQ. But anyway, now it is full. It is full. Okay. Rear is max size plus 1. Of course, you can not have max size plus 1 indices because maximum you can go is max size minus 1. Okay. You cannot even go for A equal max size because it's index out of bound exception. So therefore, A and D. Okay, A and D. A and A and sorry, A and D, correct. A and D. Third one. Which of the following statement is are correct on skipped list? Remember in skipped list we discuss some nodes can skip other nodes. So always we have this kind of a thing, but additionally you can
What
have
is
this
the answer
kind
to
of
the second one?
Sorry?
A and
Sorry?
second one answer A and E.
No, A and D. A and D.
Okay, sir.
Right. Third one. So skip list is like that, right? So you can have like this, or sometimes you can have like this, bigger steps. So if you are going far away, you can use the skip things to reach it faster. Okay, reach it faster. And usually these are double linked lists because sometimes you need to come back. Okay, right. Non-sequential searching can be done with a skip list. Non-sequential searching. You go like that. Right, you go like that. Sometimes you need to come back because you reach somewhere here, but what you're looking for is here. So, but still it is sequential, right? Sequential means you go like this. But anyway, we can skip also, right? Skip is still sequential, but sometimes you need to come back. Can we think of sequence? I'm not very sure about this. This is very confusing, okay? Because sometimes we go like that, and sometimes you need to come back. But I feel like still it is sequential. But can we consider skipping as a sequential is another problem? Okay, I'm not very sure about that. Okay, skip list is a linear data structure. I don't, still it's linear, but this is something really confusing for me. Can we consider it as linear? Because you can skip and go also. Okay, this one is terrible question for me. The third one, skip list
So,
can be, sorry?
sequential means there have to be a pattern, right? So when we
No,
skip
sequential means you
the
go one after the other, like this. So remember in programming, this is called sequence selection. Okay. So sequence means you go one after the other. Selection means you go conditionally. So if you take the mathematical meaning, yes, there should be a pattern. But sequence is overloaded term, right? Overloaded term. So that is why this is not sequential. This is okay because you go here and there, right? Not one after the other. Go like that, go like that. So this anyway, it's overloaded word. Okay, so different meanings are there, but usually sequential means you go like that, not go like here and there. For example, graph is not sequential because there are multiple parts. Okay, so sequential means always go like that, passing the things. But here also you can go like that, but you can skip. So therefore, can we consider it as sequential? That is my concern. Okay. Anyway, I'm not very sure about these answers. Skip list can be used to implement priority queue that work very well in multi-threaded environment. Can we use a priority queue? How can we use skip list for priority list? So priority list means you insert, but you take the priority value. That also I don't think, right? Can we use skip list for priority list? Priority list, sorry, priority queue. So you take the high priority. Again, I'm not very sure, okay? An array is an efficient data structure to implement a skip list. No, right? Because we can implement skip list usually using linked list so that we have the flexibility to link in different ways. Array is more suitable for normal list because you go from like this. But if you want, you can go from zeroth element to fifth element and so on as well. I don't know. This is all answers. I'm not very sure. Okay. Anyway, I'm not sure about any of these answers. All are fuzzy for me. And anyway, what is the answer given? C. C means two, two, is it two and three? One and three only. Non-sequential. So they have taken it as sequential, most probably because we can skip and go, and also sometimes we need to come back. Third one, skip list can be used to implement priority queues. That means it can be used for priority queues. Okay, let me ask that from ChatGPT because I'm not very sure about this question. Okay, maybe ChatGPT has better explanations. Non-sequential. Skip list use multiple levels of forward pointers, letting you skip over many elements at once. So it says because you can skip things, right, rather than going to the next, next. It says uh, non-sequence. Anyway, that is not debatable. Anyway, examiner's answer is also include that one, right? Third one, examiner's answer is C, that is 1 and 3. Yeah, therefore that is fine. Okay, I think that is not very debatable. 2, skip list is a linear structure, although the bottom level is linked list. Yeah, linked list is linear. Skip list is a multi-level probabilistic structure, not a simple linear data structure like array or linked list. So the thing is, though we have a linked list, still because you can skip and go, they consider it as non-linear structure. Okay, I think that is also fair. Then the third one, examiner has taken correct, right? Yes. Skip list can be used to implement a priority queue. How do you use skip list for priority queue? That is my concern. Support efficient insert delete, but it has not explained. Maybe you can ask how to implement priority queue using skip list from ChatGPT and double check. Okay. And fourth one, an array is an efficient data structure to implement a skip list. It says no. I think the best thing is go for linked list, right? Yeah, because we need to dynamic node heights and so on. I think that is fair. That is fair. But let's ask how to create priority queue. Create priority queue using a skip list. Maybe ChatGPT will not be able to explain it clearly because it needs image. Then you search it in YouTube. Okay. Uh, priority queue support. Insert, find min, delete min, blah blah blah. Key is the priority. Value is the element. Multiple forward pointers. Insert operation. Skip list search, find the correct position for the priority. Randomly choose the node side, blah blah blah. Anyway, just spend a little bit of time because it looks a little bit more complex, right? I don't think I can understand it quickly. Maybe you can have a bit of a chat or go to YouTube and see whether you can get it. Okay. Fine. You can see ChatGPT is giving me one line exam answers also. So ChatGPT has a hint that maybe I am preparing for the exam because these screenshots are exam questions, right? So that is you can see ChatGPT is know the context. Maybe this guy is preparing for the exam. That is why this guy is paste in these exam questions or something like that. Because that is why ChatGPT say I can even give you one line exam answer, right? Fine. Anyway, just double check that, okay? When you have time. Right. Fourth one. Consider the following pseudocode. When the execution is finished, what would be the final content in the stack? So these are the typical questions you get, right? These are not that difficult. Only thing is you need to do it fast. So you have create a stack and we are in a for loop. In starting from 0, uh, as long as it is less than 19. Now first I is 0. If I mod 3 is 0, 0 mod 3. When 0 divided by 3, the remainder is 0, right? Because nothing and nothing remains. Right? Nothing for 0 divided by 3 is nothing and nothing remains. So therefore I say true. Therefore I'll come here, push. So now 0 is pushed to the stack. 0 is pushed to the stack. Else if, because if he's satisfied, I don't go for else if. Then I is 2, I is 1. 1 mod 3. When 1 divides by 3, the remainder is nothing, remainder 1. So it's not 0. Okay. It's false. I mod 4 is 0. 1 divided by 4, remainder is not 0. Therefore, I will not come to if. Else if I mod 5 is 0. No, it's not divisible by 5. 1 is not divisible by 5 and remainder is 0. No. So therefore, I will not pop also. So here we check whether it's divisible by 3. Is it divisible by 4? This is 3 or 4. This is divisible by 5. Right? So 1 is not satisfying any of those, right? 2 is not satisfying any of those. 3 is not satisfying any of those. 4 mod 3 is not 0, but 4 mod 4 is 0. Right? So therefore, we push it. Right? So then 5, it will satisfy this. You pop it. You pop it. So now we are in 5. Pop it. Pop it means now it is 0. Okay, 0. Then 6 divisible by 3.
Can you start from first?
Sorry.
Can you do it from first and show?
Now, first one is 0. 0 is not divisible by 3. Right? Not by 4. Sorry, 0 is divisible by all these things. Right? Because when you divide 0 by 3, remainder is 0. Right? Remainder is 4. Remainder is 5. So therefore, it satisfies everything. So therefore, it first satisfies this. So therefore, I push it. But 1, 2 doesn't satisfy this. Right? 1, 2 doesn't satisfy this. But 3 satisfy this. Right? 3 divided by 3 is 0. So therefore, we can push 3, right? Yes, first we can push 3. So 0, 3. Then we push it. 4 satisfy this. We can push 4 also. Then 5 satisfy this. So therefore, you need to pop it. You need to pop it. Pop value. Now we are in 5. 6. 6 divided by 3 is 0. Yes, 6 is divisible by 3. So therefore, we need to push 6. Right? 0, 3, 6. 7. No, none of these are satisfied. No push, no pop. 8. Satisfy this. You push it. 9. Satisfy this. 10. Satisfy this. So you pop it. So 9 is lost. 0, 3, 6, 8. That is 10. Then 11 not satisfying any of these. 12 satisfy this and this both. You push 12. 13 doesn't satisfy any of these. 14 not satisfying any of these. 15 satisfy this first. So therefore it will push. So therefore it won't come here because it satisfies this. Okay. That is 15. 16 satisfy again this. 17 doesn't satisfy any of these. 18 does not satisfy any of these. 19 doesn't satisfy any of these. 20 satisfy, sorry, it's only check up to 18. Right? So now the answer is when the execution is finished, what would be the final content of the stack? 0, 3, 6, 8, 12, 15, 16. Okay, so not this, not this, not this 0, 3, 6, 8, 12, 15, 16, 18. 18 does not satisfy this. Does not say, yeah, 18 must also be there. So this is the answer. This is the answer. This one has less data, right? So the answer must be E. So basically, if it is divisible by 3 or 4, you push it. If it is divisible by 5, you pop the last push one. If not, nothing happens. Okay? If not, nothing happens. So I'll go for E. Yes, C. Okay? 5. The number of elements in adjacent matrix of a graph having n vertices is, that is easy question, right? So if you have adjacent matrix, say something like this, A, B, C, D, you have A, B, C, D, A, B, C, D, right? So these are our elements. So then A to B, 1, right? A to C, 1. A to B, 1, A to C, 1, no A to A, no. So then B to D1 and so on, right? It's if you have n nodes, it's n by n matrix. N by n matrix, right? Number of elements in the adjacent matrix, n squared. N squared. So that is easy question, right? 5 answer is A. Yes, A. 6. Okay, let me, because when I heard so many things, it start flickering. Unfortunately, it start flickering. I think that is a bug in Edge. It happens maybe after some recent upgrades. Or maybe I can close it and open it. Okay. Right. Question number 6. Which of the following statements is are correct regarding sorting algorithms? Sorting algorithms. Insertion sort makes no more than n log n pairwise comparisons. No, insertion sort is n squared algorithm, right? So this is not n log n algorithm. So it's actually worst case, it will search for n squared comparisons. Okay, not n log n. N log n is related to quick sort, merge sort, and binary heap sort. B, merge sort is not an in-place sorting algorithm. In-place means we do it in the using only the array. Right? We just use the array. Right? For example, selection sort, bubble sort, because we just swap in the array. Right? Selection sort, bubble sort, insert sort. If you just use one variable, that is fine. So you just keep it to the one variable and put it, that is fine. But remember in merge sort, we need to merge two arrays to another array, right? Because you can't just merge two arrays into the same array. So therefore, this is uh, not a in-place sorting algorithm, right? Not in-place sorting algorithm. But quick sort is, right? Quick sort is because you just swap things. But this is your, actually that is why though merge sort is uh, n log n, it take additional memory. Okay. So therefore I will say not an in-place sorting algorithm. Yes, merge sort is not in place. You need additional arrays, right? Merging it to additional arrays. C, selection sort is not a default stable sorting algorithm. Oh, what is this default stable? Let's keep it, okay? I'm not sure about that. Default stable. The best case runtime complexity of merge sort is ON. Best case complexity. I don't think we can do it in ON, right? So if it is already sorted, what happens? Already sorted. Anyway, you need to break it, right? Break it, break it again, because we have no idea. I don't think we can do it in ON, right? Then again, we need to merge it, right? I don't think, right? Because anyway, though it's sorted, still we need to break it and merge it, right? Recursively. I don't think so. Because it says best case, right? Even best case, I don't think we can do it because anyway, we need to partition and merge it. The worst case runtime complexity of bubble sort is n squared. Yes. Bubble sort is n squared algorithm. Right? What is this default stable sorting algorithm? Anyway, let's first look at the answer. I'll go for B and E. I'm not sure about C. B, E correct. Yes, examiner has taken C also. That means this is a default stable sorting algorithm. Okay, let's ask ChatGPT. I'm not very sure about that. What is mean by default stable sorting algorithm? I'll say explain using examples. Default stable. This phrase trips a lot of people up. Let's unpack it clearly and the examples. Stable sorting algorithm is one that preserves the relative order of equal elements. If two items have the same value, that means if your data has same number twice, right? Say 50-50 twice. Or sometimes these same number can swap. So okay, but these can be two different objects, right? Because sorting wise, maybe you have 50 and 50 here. Maybe the expectation is at the end also those same numbers must be in the same order, or maybe the two different objects. Okay, so that means if this is 50 and if this is 50, in the sorting algorithm also this 50 must be here, this 50 must be here. Okay, not this 50 is here and this 50 is here. I think that is what ChatGPT is explaining. Okay, okay. Uh, what does default stable sorting means? The sorting method used by default is by language or blah blah is stable. It uses, yeah, it doesn't change the order of equal elements. Okay. Uh, right. So they have given example. You can see 290 values. So still A must be left side of C, not C is left side of A. Okay. Right. So this is wrong. Right. Because your A is here. Right. After A you must have C. Okay. Now you can see A has gone after A. Right. So it says now this is for the exam. All these are default or stable. Bubble, insertion, merge, count. I don't know what is count. Radix. And best thing is try to remember the not default stable one. Selection sort, quick sort, heap sort. Okay. So just make a note of that. So these three sorts are not preserved in the relative order of same values. Relative positions of same values. Selection sort, quick sort, heap sort. So if you analyze the algorithm, maybe we can understand why happening, but let's for the time being, at least remember selection, quick and heap sort are not stable algorithms. Okay, that means same values can be change their positions. Okay, right. Just make a note of that. Okay. Right. Consider the following function, func1. What is the above function intend to do? Deleting an element from the linked list, inserting a new element into the linked list, reversing the element in the linked list, searching for an element in the linked list, sorting element in a linked list. Okay. Let's see what it try to do. Node pointer is head. Now it's pointing to head. Okay, let's say this is our linked list. And this is looking at null. This is our head. Pointer is looking at this. So pointer is now also looking at head. Previous is null, current is null. So previous is here, current is also null. It's searching for something, right? While pointer is not null, current equal pointer. So current come to the pointer, and pointer equal pointer goes to the next, right? Your pointer is now here, current is here. Right, now current is here. Yeah, current is here. Current is comes to the pointer, pointer goes to the pointers next. Then current dot next is previous. Current dot, what is that? Current dot next is previous comes. Current next take a previous. So current dot next is previous means now this is looking at previous. Previous is still null, right? Okay, anyway. Current dot now current is this one. Let's make it clear. Current. Current dot next is previous. That means current is now looking at null because previous is null. Previous equal current. Now previous come to current. What is this? Previous come to current. Head equal current. Head is also current. Look at the maker. Okay. Okay, let's see. We do it again. Current equal pointer. So current goes there. Current goes there. Pointer equal pointer dot next. So the pointer moves further. Pointer. I try to see what is happening. Current dot next is previous. So now current dot next is previous. So the previous is now looking at this one, right? It looks like it reversing this, right? Previous. Previous equal current. Now previous come here. Previous come here. Okay. Previous come here. And head is current. Now your head is this, yes. මෙයා මොකද මේ කරන්නේ? මේ එක එක රිවර්ස් කරන් යන. මේ පැත්තට ගිය ලිස්ට් එක ටිකක් අන්තිම වෙද්දි මේ පැත්තට වෙලා තියෙන්නේ. That is what I think by looking at this because head එක මෙහෙදි වෙච්ච head එක අන්තිමට කෙරවලට ගිහලා තියෙනවා. And මේ right? So this is basically reverse in the linked list. Anyway, it's an interesting question, right? By look of it, if you want to see it further, you can do another iteration. So then head will be here, this will be reverse. Okay. So basically it is reverse in the elements in the linked list. All of a sudden your head become tail, tail become head. Okay. Reversing answer for me answer is C. I'm pretty sure answer must be C. Okay. Yes, answer is C. That's an interesting question, right? Challenging question. So just go few iterations and see what's happening. Okay. Right. Eighth one. What is the shortest path, right? අපි මෙතනින් එහාට ඊළඟ ක්ලාස් එක කරමු. shortest path කරන්න අර මේ බැඳලා හදන්න ඕන. හරි? මතක නේද? Dijkstra algorithm. ටිකම් බලලා කරන්න පුළුවන්. MCQ හන්ද බලලා කරත් කමක් නැහැ. මේක අරගෙන බලන්න. කොයි එකතුව කීයද කියලා. හරි? එහෙම කරත් කමක් නැහැ. එහෙම නැත්නම් අපිට Dijkstra algorithm use කරන්න වෙනවා. හරි? Right. So anyway, we'll do from this point onwards in the next class because I have another class at 1:30. Okay. Right, we stop at this point, right? I will try my best to add an extra class, okay? Uh, right? I try my best to add extra class and try to finish the DSA in this week itself so that we can concentrate on. Anyway, we are going to do past paper on data management next class. Okay, right, we stop at this point.
Thank you, sir.
Okay, you're welcome.
Thank you, sir.
You're welcome.